Good afternoon, ma'am.
Good afternoon, sir. Sir, एक बार मुझे ट्रायल करवा दीजिए. Not able to see chat box when I'm presenting.
Ma'am, what FDP EICT Academy NIT MNIT Jaipur, no?
Making you co-host so that you can have the full control.
Should I change the name?
No, ma'am, no. Still we have 10-12 minutes left.
I want to have a trial before start.
Yes.
I'm not able to see the chat box.
Share. You are not finding that share button?
Share button? No, not. Yes, it's here. It's there. Screen one. Should I share screen or a window?
Just check once that everything is working fine.
Okay. Just give me a second.
Yes, ma'am. Your screen is visible.
I request, please write something on chat so that I can see it. Yes.
Your screen is visible, ma'am. Your presentations are visible.
Okay. Thank you.
For annotation, I think you will have that button for annotation. You can annotate as Ma'am, only 17, 18 participants are here. So, and still 8 minutes left.
So we'll wait, sir. No issues. We'll wait for 8 more minutes. I was just trying to present at the same time, want to see the chat. That's what the concern was. It's okay for me. I'll wait for 10 minutes. Thank you, sir.
Good afternoon, everyone. Welcome to, I think, 8th day, no? Of JP on natural language processing. So today we have Dr. Namita Mittal as our expert. Ma'am,
Good afternoon, sir.
good afternoon. So, Dr. Namita Mittal is an associate professor and associate dean student welfare in MNIT Jaipur. She is associate professor in the Department of Computer Science and Engineering. She is a recipient of Career Award for Young Teachers by IICT. Her current research areas are data science, information retrieval, data mining, and NLP. She has published several research papers in reputed international conferences and journals, and 2 books in their publication. She is a member of review committees for a number of referred journals and conferences. She is a senior member of IEEE, member of ACM, and SCRC. She has conducted various FDPs, conferences, workshops, PhD colloquiums like FIRE 2017, and GAN courses also on Advances in Data and Web Analytics 2007. She is coordinator, regional coordinating institutions for Central Rajasthan at Unnat Bharat Abhiyan, Government of India. She has also filed a patent on CHAL, the Smart Gate Analyzer, and she has also contributed a research project in design and implementation of learning activities in Hindi for school education for rural government funded by DST, and security audit of e-auctions funded by Government of Rajasthan. So welcome, Dr. Mittal, and now I will request to start your presentation.
Good afternoon, everyone. I hope I am audible.
Yes, ma'am, you are audible.
So this is your which day it is? It's around 8th day, right. So I hope that everything is going good. And you had 2 quizzes already. So some of the questions will be asked from today's lecture, that is text classification. Text classification is important. This is one of the most important tasks in NLP. It is the process of classifying text strings or documents into different categories depending on the contents of the string. Text classification has a variety of applications. Nowadays, we are seeing it, even we are experiencing every day the life, like sentiment analysis, maybe from tweet, maybe from classifying an email as a ham or spam, maybe blog posts into different categories like automatic tagging of customer queries and so on. So I have taken some of the examples from the real life examples, and I would like to have Jupyter notebook to be shared before I start up experimental part of this session. Initially, I'll cover the theory, and later I'll take the practical part. I hope it's working. So I'm going to share. My screen is visible? Is it visible? Okay. Okay, so text classification. So this is my presentation outlines today's presentation. Text classification, I'll cover what is the definition, what is the need, what are the issues. I'll cover some of the classifiers, important one. One of them is naive Bayes. I'll take 2 examples of that. Then later vector space classification, and how document representation is different from text classification or a document classification. One of important classifier is a Roorkee classifier. I'll relate it with the information retrieval. Then how do we say that yes, this classifier is good or not good, or maybe to some extent it is is okay kind of thing, that we check with the evaluating measures. Then ultimately the question being asked by the students or the general users, that which classifier do I use for a given text or for such problem, that we'll discuss. So okay, so text classification is important part of NLP, because this course is NLP, so I'll relate, because the classification, that is supervised learning, comes into data mining as well as information retrieval as well as in natural language processing. So I'll relate this lecture with the NLP. So it is a process of classifying text strings or documents into different categories. Different categories are given before in hand. That's the thing that we know in advance, that the experts are with us, and they classify it in, that is training kind of thing. Then we have a classification. If we don't have before in hand classes, then it comes to the clustering. Even apart from text classification, we can have a text clustering as well. It depends on that area or application. So what kind of variety of applications? Sorry, sir. Sorry, sir. So it is the process of classifying text strings and documents into different categories depending upon the contents of the string. So variety of applications detecting user sentiments from a tweet, classify an email as a spam or ham. This is the important area everyone wants to use it, need it. Similarly, we have different kind of blogs and posts in different categories, maybe on genre wise, on maybe of depending on the need of today's era. Like COVID is going on, this blog will go into COVID or non-COVID, or maybe some politics, election is going on, it will be related with the election or not, something like that. We use it. So this is the example I have start with the spam filtering. So looking at this email, no one can say that it's coming from where. So what makes us understand that it is a spam or ham, right? So people generally ask, how do we relate it? Being an intelligent person, means being a human, we can always identify that yes, it is a spam. Spam, it means it has been broadcasted to many, and it is for the general purpose, and we are not concerned about it. We don't want to have this in our email inbox, right? So we don't want to receive this mail because it may flood your inbox, and it's difficult to handle it. So what are the features that makes it spam, that we want machine to learn it, right? So here some of the words, some of the vocabulary which makes it spam. So these are to be identified, right? So looking at this one, we can see that from where it has come, right? So looking at this email ID and then look at the subject, looking at the contents, we can easily identify, yes, it is a spam. But how does machine learn it? That is the text classification, right? We want our machine to learn and understand that yes, it is a spam. So it should not come to our our inbox. It should go into spam, because spam are deleted by default in 1 month. We don't have to worry about it. So generally, sometimes it happens that an important mail goes into spam. So why does it happen, and how does it happen? So in case of that, the mail that is not a spam, that is a ham, important to us, but it goes to the spam folder. It means that is inaccurately identified as a spam. Machine is doing for us, but sometimes it is not correctly identified. We have to check it, right? Machine has to check it. So these are the things or the issues we'll handle it today in today's session. So in general, if we specify text classification, it is generally people ask, is it different from text categorization? No, it's same. Text categorization or text classification, they are same. We'll be using text classifiers and naive Bayes, Roorkee, KNN, K nearest neighbor, support vector machine, decision tree. These are the important thing. And I'll take the example of ensemble classifier using the different decision tree, that is a random forest algorithm, right? So we'll be covering these in theory and one in practical. So as everyone knows that classification is something related with supervised learning. It means we have supervisor or expert before in hand that classify the instances given to us before in hand with a label. Label is something class. This instance, this text will go in this class, this instance will go in this class, likewise, right? These are the instances we have before in hand. On the basis of these instance features and the related classes, we can always classify a test, right? So before in hand, we have some set of classes, a training set D of label documents. Labels means with classes we have, and this is a set of the instances and labels. Small c is a label, and all the classes C1 to CJ here we have taken, those are from the C. So no label can be beyond C1 to CJ. This is the assumption, and this is the predicate that we have to follow it. So basically what we have to do it, or we have to determine it for the instance that is a new or a test case, we have to identify it within the instances given to us with the labels. It means if we have two labels, yes and no, the test case will not go beyond yes and no. That is a mandatory thing. If we have three classes, RGB, red, green, blue, it means we have to classify our test case within these classes, red, green, blue, right? So what happen if we have a class that is none of them? That is a new thing. That is a new thing. So that goes into active learning. You may be learning very soon in another class. That is the active learning, but the class level is not given, but we have to identify that, yes, suppose we have got tiger and cat. There are two classes, but the test instance is not either the cat or not the tiger. Then where should it go? That comes in a different category. So here today we'll see only the text classification, where the test case will go within these classes given to us before in hand. So how text classification and document classifications are different. Document, it means we have some set of characters, we have some set of words that makes a document, while text may be anything. While text may be maybe a mail or maybe blog or something, and maybe SMS. So document, it means it has some kind of words together. Here you can see from the example, this is my pointer is moving. I hope it's visible. It's planning, language, proof, intelligence. It has the words, and we have some categories: ML, planning, semantics, garbage collection, multimedia, GUIs. So training data is already given to us, learning intelligence algorithm and reinforcement network, and we have categorized that they are the part of ML. So on the basis of these features, these are nothing but the features. we have categorized into ML, machine learning. Similarly, we have planning, temporal reasoning, plan, language. They are into planning. Programming, semantics, language proof. They are into semantics. Garbage collection, memory, optimization region. They are into garbage collection and so on. So all these are nothing but the features of a class. These are the classes. Here we have ML, planning, semantics, garbage collection, multimedia, and UI. So you may be wondering that what is this AI programming and SCI now? So within a class, we can again subclassify the class. There is a hierarchy of classes. So whenever ML, the particular words, those are part of ML, ultimately they are going to AI and as well as planning. So it depends on the need or the application that how do we classify. So before in hand, we have to identify what are the features belonging to which class. There may be several classes as well, and there may be subclasses as well. Together, subclasses make a class. So some examples I'll be quoting today that assigning labels to document of web pages is nothing but a classification example of text classification. Here the labels may be finance, sports, and there's a third category, news. News may have again subcategories. The word, within word there's Asia, within Asia there's a business. Similarly, we can have news may have different categories like word or nation. Nation can have other states or districts and so on. Labels may be genre as well, editorials, movie reviews, news, etc. Labels may be opinion on a person and a product like hate and neutral. Labels may be domain specific as well. It is interesting to me, it is not interesting to me, maybe 0 and 1 we can have, or maybe true and false, maybe negative, positive, anything can be taken depending on the need. So this block contains adult language. This block doesn't contain adult language. It's like 0 and 1. Like language identification, there's another way of categorizing or classifying like which language it belongs to: English, French, Chinese, Hindi, and so on. Search verbal is about Linux. It's not about Linux. This versus not. Link spam and not link spam. Many search engine functionality uses classification. Given a description, description is nothing but the number of words, or a document here we can say belongs to X, and we need to determine Y. Y is nothing but a class, right? So if we find the, if I say Y is equal to F of X, so F of X are the input and F is nothing but a function. So here in this case, F is nothing but a classifier. We are sending our contents to the classifier and we are having some class out of that. So here that F is classifier, and the F may be anything, and X may be anything. X is a set of X1, X2, Xn. These are the parameters. So how do we reach to these parameters? How do we pre-process a document such that we reach to the parameters or the features? That's the question. So class is the most appropriate for document. Language identification like classes English versus French. The search engine is also using this classifier. For example, automatic detection of spam pages are being used. So many search engines are using it, this classifier, and giving us the results such a way that we are only getting the non-spam in inbox, spam in spam folder in case of email. Similarly, if we ask a question in English, then the answers are given in English. If we ask a question in French, then answers or the documents searched by the search engine are in French. By default, it's Google, but there may be any search engine. So categorization or classification, I said that they are same in terms of text classification. So what is given to us and what is to be found out? That's the question. A representation of a document D. Now the question is how to represent text documents. That's the text documents. We have to find it out the features. What are the important terms or the words? Those are important for the text to be classified. Usually some type of high dimensional space is back of us. A fixed set of classes are C1, C2, Cj, and we have to determine the category of D. YD is equal to say where YD is a classification function, right? So C is nothing but the class. Those are already given to us. The class that is to be detected cannot be beyond this range, and the document where that is what it has been passed to the function, that is f of x. Here we have taken y, and we are passing d and getting c. So we need to build a classifier, and there are lots of classifier already there. We have to choose which classifier is good. Even we can have a hybrid kind of thing, that we can use this classifier partly and this classifier partly. And sometimes we can give the weightage that we'll see in ensemble classifier. So looking at a document, we have done it. Now the question is, do we need to do it always by machine? Can we do it manually? Yes, the answer is yes. We can classify manually, but it's difficult, because when we have used database, it's difficult to do it. But manual classification is supposed to be accurate when job is done by expert. When the data size is limited and the team is small, then yes, the results are good. But it is difficult and expensive when the data is to be scaled up. Yes. So we need to have the automatic classification. It means we want machine to learn it. How do we do it? Got it? So these are the hand-coded rule. When we do it by machine, automatic, then some rules are to be defined. Those are known as a hand-coded. Someone writes the rule. Like in C program, what we do? We need to find which number is greater than A, B, C. There are 3 numbers, and which is the greatest one. So we write some rules. Those are nothing but the hand-coded rules. So one technique used by new agencies, intelligence agencies, or widely deployed in government and enterprises classification methods. Vendors provides IDE interface kind of rule for writing such hand-coded rule that makes it a bit easier. Otherwise, it's difficult to have many rules together, and they have to be checked first, tested first, later they can be implemented. So when we write our rules hand-coded, then the classifiers are known as hand-coded rule-based classifiers. Commercially, systems have complex query languages. Accuracy can be high if rule has been carefully redefined over the time by the subject experts. So the constraint is, how do we find the subject expert? Means about the domain. Suppose I have a data about the medical. So I need medical experts. Those can write the rules. They can see it is working well or not. So that's a bit costly affair. That find the domain experts, and they agree to write the rules, and they agree to see the instances, right? So this is the biggest issue. Being a researchers, we are facing that first thing, that yes, we know the problem definition. This is a problem, we want to solve it. But how do we get the test data? How do we get the data? And then that to be labeled. Someone has to label it, that someone should be there with us to say, yes, this instance belongs to this class, this instance belongs to this class. So building and maintaining these rules is expensive, but still there's a trade-off that sometimes it's important to write it without worrying about the expensiveness. So the basic definition of text classification is we have in hand document D, a fixed set of classes, a training set D, capital D, of documents which with a label in C, C1 to CJ are already there. And that data should be non-skewed. If we have 2 classes, it doesn't mean that, say, out of 1,000 instances, and 900 are going in C1 class, and remaining 100 documents are going in C2 class. If you have 2 classes only, C1 and C2, there should be non-skewed, means labeled balanced data. It is known as a balanced data. We can have a 50-50 ratio, we can have 60-40 ratio, some kind. It's not like 90-10. So that is again a necessary part, that we should have a data such a way that it is balanced. They don't have a biasing towards the classes. A learning method or algorithm which will enable us to learn a classifier Y. That is what we want. That is to be determined. This is the test data. What is to be classified? Suppose that email comes, we have to identify it. It will go to the spam or ham. So that is to be labeled. So for test document D, we assign it to the class out of the class label C1 to CZ. So as we have understood that it is a supervised learning, whenever the classification comes or a regression comes, it means we are working on the supervised learning. We have some training data, those are labeled. I'll take one example of naive Bayes. Naive Bayes is a simple and very common and is good for text classification. It depends what kind of data we are working. So we choose classify. I'll tell you in the end, then how do we choose it. K-nearest neighbor algorithm or a classify is very simple, it's powerful, and we don't have to have the training. We have to have some instances, those are labeled. That's why this is known as a lazy learner. At the time of identifying a test case, the work starts. Well, in case of naive Bayes, we have to have some training that is to be trained. The model is to be trained. Support vector machine is very famous. It's powerful as well, but we have to have some vectors and some complicated is 2D. The many dimensions has to be converted into less dimension space. Many more methods are there. One of them is Roorkee. Roorkee is very famous for text classification. Here we have some vector space models and centroids are to be computed. So we'll see example of Roorkee as well. In the Roorkee, there's a relevance feedback and some probabilistic model is used. Centroid is computed. And other things are also, there are many commercial systems use a mixture of these models. We have just seen, we can have this. Apart from that, there's a decision tree model. As the name says, trees, collection of trees make a forest. So which trees are to be considered, which branches of the trees are to be considered at one time, reaching to some conclusion. Some conclusion means classes. So that is known as a random forest classifier. It is also an ensemble classifier. So I'll take the example of random forest classifier. So this is the bag of word representation. You are seeing that this is a y. Y is a function, and we are passing some data. This is input, and ultimately we are getting C. C is nothing but output. That's the class. This is the purpose. And these are the words. Basically, these are the bag. This is the bag of words. So which word is useful, which is not useful, making our function to reach to the classifier or the class. This is how we can represent out of many words. Look at this. These are the many words. I have taken only the limited. So here in this one, the great appears twice. Love appears twice. Recommend one. Laugh one. Happy one. This is nothing but the frequency of a word, right? So what about the other? Those are there. I am, and I, who, has, not. What do we do with that? That's the question. This is known as a pre-processing. So pre-processing is a very important part of text classification. Here, first of all the documents or all the text are to be pre-processed. Only the important words, those are important in such a way that those are not very frequent words and those are very less frequent words. There are two terms, frequent words and less frequent words. Frequent words, those are appearing in every document. So they are not concluding or making importance in classification. If I say, if I have some words, those are appearing in any documents, say A, N, D, I, U, V. Yes, without them, we can't survive because those are the part of the vocabulary. Without vocabulary, we cannot make a sentence. But they are not contributing in getting the class because they are appearing in this. Those are known as the frequent words. Sometimes we have some non-frequent, rarely appearing words. Yes, they are making sense. They are contributing to the classes. Now the question is does it matter that grade is coming twice, or this word is coming twice, or another word is coming tens? Yes, that is a term frequency. So we'll see one by one how do we do it. So feature selection, these are the features, nothing but the features: great, love, recommend, laugh, and how do we select them? So if you have large number of text collections have a large number of features. जितना ज़्यादा texts होंगे उतना ज़्यादा number of features होंगे. Generally unique words, if I have 10,000 documents, I assume that 10,000 to 1 lakh or 10 lakhs words are unique words. So unique words, it means they are not non-repetitive. Once it has come in one document, it will be considered only once. That is the unique words. Selection may take a particular classifier feasible. Some classifier can't deal with 1 lakh features. So we have to reduce the features so that training time taken is less. Training time for some method is quadratic, means polynomial, or in the worse in the number of features. As the number of features are growing, is taking too much of time. So we have to again take the trade-off that the number of features are important or time is important. So sometimes we reduce the features, sometimes it's okay with the time. We have to take all the features because the reducing numbers may lose sometimes the information. So it makes runtime model smaller and faster. It can improve generalization. Generalization is nothing but related with the performance. It can improve the performance if we take all the features. It eliminates noisy features. It means they are not contributing in getting the class, but just improving the increasing the number of features, and avoids the overfitting. So now question is what we mean by overfitting. Overfitting and underfitting, there are two terms. Underfitting is like loosely fit clothes or a attire of a person. So every can be fitted into it, right? Underfitting, it means the training is not done well. Overfitting means training is done well, but such a way that whenever the new instance comes in, if it's not exactly fitting, but it's like a 10% or 5% margin, then also it's not reaching to the exact class. Overfitting, it means if I have 50 students in my class, I have taught them that these are the lessons we'll be covering and not related with that. These are the only tests and they are fit for that. But the question comes little bit out of the syllabus, but related with that the student will not be able to get the test clear. That's the underfit. That's the overfit. And if I say that underfitting is like many students are there in the class, and some of the topics are taught to them and some of the topics are not taught to them. They are underfit. They may do well for the related topics, may not do it. So we'll see related terms with the overfitting and underfitting is bias and variance. If you have any question, you can ask in chat. So far, I can see there's no question. So feature selection is like which feature is important? Should I take all the features? If no, what feature should be important? What should I take? How many number of features? Number is to be taken well. How many numbers and what features? Just suppose the out of 100 features, I'm allowed to take only 10. So which 10 are good? So these are the two important questions. The simplest feature selection method just use the commonest term. The first thing is the common in every document or most of the document, that is a commonest term. Should I take it? This is an important question. So as why we are doing it so? We are doing to find the best class, right? But this is not contributing, the common feature is not contributing to the class because it's coming in every document. So we can remove it, right? Commonest or common term. and no particular foundation is given. If feature selection is necessary, then but makes sense why this works. They are the words that can be well estimated and more often available as evidence. In practice, there are 90% as good, better methods. So feature selection methods are standard. Those are available in the Python library as well. We can use it. But if manually I have to do it, I can remove the stop words. I can take the rare words. Suppose in one document, the term is like zero freezing. The one document, and it's reaching to a document that is say ice, right? So we can easily say that yes, zero freezing is related with ice. The only document, only one term is easy to understand, is easy to reach to some class. The important classifier that starts from Bayesian learning, that is a mathematical concept, has been used, Bayesian naive-Bayes algorithm. So Bayesian algorithm that calculate explicit probability for hypothesis, such as the naive-Bayes classifier. So it's good classifier, generally people use it. I'll take the example. Problem of learning to classify text documents such as electronic news articles. For such tasks, we can use it is most effective algorithm amongst many other. So here we have some issue that is of independence. It has an assumption that the events those are occurring are independent of each other. If this assumption is satisfied, then only we can proceed it. Right. So in terms of text classification, if I have a word data mining or information retrieval, it has been assumed that data and mining are independent of each other. We cannot say whenever the data comes in, the mining will come. They are independent of each other. If I say a word is mining and data and mining, they are same. There's nothing to explicitly say about the order, right? So sometimes it doesn't happen. We have to have some kind of correlation between the words. Then this naive-Bayes classifier cannot be implemented. If two events A and B are independent, then the probability, that is the prior probability, that whenever B has already happened, what is the probability of having A? Because A and B are independent of each other, so it's equivalent to probability of having both together is A intersection B divided by probability of B. And probability of A intersection B is nothing but PA and PB, because they are independent of each other. If they are not independent of each other, we cannot write it, right? As we are writing that P intersection of B is equivalent to PA dot PB. So PB and PB, probability of B and probability of B will be cancelled, and it will be equivalent to P of probability of A. Probability of A by B is nothing but probability of having A when B has already occurred. Got it? So probability of A by B is nothing but P of A. This is what it has been proved. This is the basic assumption. My pointer is moving. So here we have converted this into this using the assumption that B and A are independent of each other. Getting? So in general, for any ones, A1 to AN, to be independent, there is a chain rule. Then if I write probability of AI intersection probability of J can be written as probability of AI into probability of AJ, and I and J from 1 to N. It may be anything. So if you have more than 2 events and I write probability of A1, I am taking I is equal to 1, J is equal to say 2, and K is equal to 3. A1 intersection A2 intersection A3 is nothing but probability of A1, probability of A2 and probability of A3 multiplied by. So this is the assumption because they are in the assumption is satisfied because they are independent of each other, right? The conditional probability is again probability theory is used here. Is a measure of probability of an event given that another event has already occurred, and they are independent. It doesn't mean that it happens. So this will happen or this will not happen, right? If the event of interest is A and event of B is known or assumed to have occurred already, that is the conditional probability. So it is written as P A by A B. So this is probability of P A by B is equal to P A intersection B divided by probability of B. If you have a question, I can take a break and answer it first. So this is again when we have more than two events, we can have chain rule for conditional probability, as we have discussed. So ultimately, look at this, my pointer. Probability of A1 intersection probability of A2 intersection of probability AN. How does it happen? Probability of A1, probability of Markov chain, or you must have done in NLP before that. So it's like probability of A1, probability of A2 by A1. Sequencing is a sequencing kind of thing. Hidden Markov model is NLP is using it. Probability of A3 is by probability of A2, A1. If it is AN, then having the probability of A1 n minus 1, comma n minus 2 up to A1. Correct? So if I take an example, what is the probability of having thunder, rain, and lightning when is equivalent to having the probability of thunder when lightning is already happened? This event, there are two events A by B. It means probability of A and what's the probability of having the rain when the lightning has already happened, and that's equivalent to probability of rain. So how do we apply in text classification? That's the question. These are the basic mathematics of probability, and then we are applying these things in text classification. So here the events are like words, text, information retrieval. What is the probability of having information when retrieval has already happened, or vice versa? What is the probability of having the retrieval when information is already just before that? So that's what we have to check it. How many numbers we have to take in before, because in text classification or NLP, there's a very important issue is the word sense disambiguation. It means what are the words before, what are the words appeared before this term, what is the context of this word, what will be the context of this word when the next two words are this. So because one term may have many meanings, which meaning is to be considered? It depends on the context of the words those are appearing before and after the words, right? So this is the Bayes rule, and using this Bayes rule, naive-Bayes classifier is designed. Naive-Bayes classifier is simple, and text classification has been done. Means it has a popularity for the text classification as well. It's simple. So here the conditional assumption is again that the words are independent of each other. So looking at the example, which class is to be chosen out of many classes given as a training classes? Which class is good for the test instance? That is the task, that is the objective. So here you can see the Y cap. Y cap is the class to be predicted, and we have to check out of many arguments or many features or many attributes of an instance. Instance is nothing but a document or a text. Suppose we have got 4 attributes, A1, A2, A3, A4. How many times the value of A1 is this when class is this? So we can have n number of classes. For every class, we have to check this, that number of classes and number of attributes. So using the example, we can check it. So this is the example number 1. You can note I have taken it from the standard book, Vipin Kumar. I have given the references in my slides later. So the credit of this slide goes to data mining Vipin Kumar. Here we have got 4 attributes: give birth, can fly, live in water, have legs, and 2 classes, mammals and non-mammals. And total number of instances are 20. So look at this 20. 20 is being used many times. It means number of instances we are having as a training set is playing a very important role. Instead of 20 is set to 100, then the thing is different. Now, how many classes in this example? 2 classes, mammals and non-mammals. How many instances from mammals class? That is to be counted. So if we have thousands of instances, do we need to count it? Yes. That's why we need automatic classifier. It's difficult to do it by hand, manually. So out of 20 instances, 7 is from mammals and 13 is from non-mammals. You can count it very well. Look at the first attribute, that is name. Name is nothing to contribute to class. It's just a name. Like if we say serial number 1, 2, 3, 4, 5. It's nothing to do with the classification. Classification issues are related with the attributes. Those are independent variables, while class is a dependent variable. Class depends on the independent variable. These are give birth, can fly, live in water, have legs. So what is the value of give birth when class is mammal? What is the value of give birth when class is non-mammal? These are to be calculated. So this is again all the classes for different attributes. This is to be calculated. So using the formula, that is to be checked. Now, what is the logic behind it? What we are objecting to do it? This is the question. Look at this, my pointer. Give birth is given to us, that is yes. Can fly is given to yes, that is no. Live in water is given to yes. And have legs, these are features, is no. If these attributes are having this value, in which class this instance will go? That's the objective. The question mark here is the objective. This is a simple example. It's not text classification. I'll take the example of text classifier to make you understand of data mining, name-based classifier. How do we do it? So here all the values of attributes are discrete. There are 2 types of values, maybe discrete or continuous. Simplest is a discrete. Discrete is, it means like yes and no. Like you can see in live in water, there's apart from yes and no, sometimes is also a value. So live in water has got 3 values, yes, no, and sometimes. Have legs have 2 values, yes and no. What if we have, say we have one more attribute, say temperature. For example, we have one more attribute, that's the temperature, and temperature has a continuous value. Then how do we deal with? So that's again it's a different issue. We'll take one example. So this is the simplest one. How do we find that this instance will go in which class? Either as a mammal or non-mammal. So look at this. A is attribute, M is mammal, and is non-mammal. These are the 2 classes. There may be several classes. For every class, we have to find it. So maximum probability we have to find for this instance. And the maximum probability of class will belong to this class. The instance will belong to the class having the maximum value. So what is the probability of having the mammal, being in mammal when this attribute, when the value of this attributes happen? So this attribute, first attribute is say give birth. We start from left to right. First attribute is give birth, right? So this is the instance we are finding in which instance it will go. So 6 by 7, how many instance of mammals are there out of 20? 7. Mammal, 2, 3, 4, 5, 6 and 7, right? So now my question is, what is the probability out of 7 when give birth attribute is having this yes? I'm taking this yes from this instance. So look at this. This is mammal and give birth is yes, 1. This is a mammal and give birth is yes. This is 2. This is mammal, give birth is yes. This is 3. This is mammal, give birth is yes. This is 4. This is mammal when give birth is no. So this is 1. This is mammal when give birth is this. Yes, that's a 6. So total 6 when mammal is, the class is mammal and give birth is yes. Out of 7, total instances was 7. 1 was of no. So these are the 6 instances out of 7 when give birth was 7. Give birth was yes. Sorry. The next is can fly. Next is can fly. Can fly is again is asking for no. Here look at this. This is no. And out of 7 mammals, how many instances are having no for can fly? This is first 1. This is 2. This is 3. This is 4. And this is 5. And this is 6. This is 6 by 7 times when class was mammal and can fly was no. Similarly, we'll do it for live in water and have legs. So this is the value when we multiply it by 0.06. Similarly, we'll do it for non-mammals. All the attributes of this test class will be checked. The total non-mammals cases are 13. Out of 13, 1 is there when give birth is yes. Non-mammal, give birth is yes. It is not there. It is not there. It is not there. It is not there. Yes, it is. Yes, this is yes. We are looking for yes only because we intend to find the instances those are qualifying these values, right? How many times? This is yes when class is non-mammal. This is 1. So it's coming 1 by 13. Similarly, we'll do it for can fly. Similarly, we'll do it for live in water and have legs. So when we multiply using the formula, we have seen the formula in the last slide. So it's coming 0.0042. Got it? Then what is the weightage of being a mammal? Out of 20 classes, 20 instances, what is the weightage of this mammal? Is nothing but 7 by 20. Probability क्या होगी? Out of 20, how many times is appearing? Mammals? 7. Similarly, non-mammal is out of 20, 13 times. That's the weightage. No? So it's not that skewed. Non-mammals are 13 times and this is 7 times. What if all are in non-mammals? Then that is a skewed data set. We don't believe on that because that will lead to always non-mammal. Whatever we do, it will be always non-mammal. Got it? So this is not a skewed data bit, it's a balanced data bit. So again, this value, first value is multiplied by probability of being a mammal. That is 1 by 20. So it's coming out of 0.021. The second one is 0.004 into 13 by 20, that's 0.0027. So which one is greater? Which one is greater? The first one, 0.021. That's the probability of being mammal. So answer is mammal. This is the concept. Using the numerical example, I try to make you understand that this is the concept behind naive-Bayes classifier. We have to find the maximum likely of probability. So if we have more than 2 classes, what we have to do? We have to do it for third class as well, fourth class as well. And out of all the classes, we have to find which is the highest probability. So instance will go in that probability. Here only 2 classes and the higher probability is of mammal. So this instance will go in a mammal. Got it? So if we can check it by chance, the same attributes values are already there in the training. We can check it. So give birth is years. This is years. My pointer. Cat के आगे देखिए. No, it's not there. Yes, no, yes, no. Yeah. First is yes. Leopard कितने देखिए आप? Please check it. Is yes. Can fly is no. We are asking for no. Live in water is yes. We are also asking for yes. And have legs is no. Oh, am I doing right? This is leopard. Yes. No. Yes. No. Am I right? Leopard is yes. Is no. Yes. Live in water. Yes. And no. Getting it? And its class is non-mammal. But we reached to conclusion that it should go in the mammal. Getting it? So what do you think? What's the problem behind it? The problem is that other instances making the contribution. Somewhere the similar instances, similar attribute values are having a different one. So out of many instances, one may be correct or may not be correct. The same instance may be somewhere else as well. So look at this dolphin. It is yes, we want yes. It is no, we want no. It is yes, we want yes. It is no, we want yes. We want no. Dolphin, it's mammal. So that way is true, right? So somewhere we can say the earlier one, that was the leopard, was non-correctly labeled. Non-correctly labeled. That's why we need many instances. This is a small data set, 20 instances only. If we have many data set, so this kind of error may be rectified, may not be used. I hope it's working. So look at another example quickly. Here we have 14 data sets and 4 attributes. Those are making contribution independent. Day is not contributing. Outlook is contributing, temperature, humidity, wind. And play tennis is nothing but a class. Class has got 2 labels, yes and no. Right? So depending on the test case, we have to compute the probability. So looking at this, we have new input set is to be classified as, we need to find outlook is sunny, temperature is cool, humidity is high, wind is strong. Right? So first we have to calculate conditional probability of each input parameter given each of the classes, as we have done earlier. What is the value when play tennis is yes and outlook is sunny? How many times? Play tennis is 9 times and play tennis is no. Play tennis is no 5 times. 9 plus 5 is 14. So these are 5 times 1, 2, 3, 4 and 5. And yes is 9 times. So this is what we have calculated first. Now we are checking what is the possible values of outlook, sunny, overcast and rain. 3 values. We'll check for three values of outlook. Then temperature is hot, mild and cool. 3 values. Humidity is high, normal. High and normal. 2 values. Wind is weak and strong. 2 values. So for every value of attribute, we have to check it. Outlook is sunny when the label is yes. Outlook is sunny when label is no. Right? Because in the question, outlook is sunny is asked. So we are worrying about outlook is equal to sunny. This is the question. This is the test case. Temperature is cool. So we'll see only about the cool. What happens? What is the probability of having play tennis is equal to yes when temperature is cool? When temperature is cool and play tennis is yes, is 3 by 9. Similarly, otherwise is 1 by 5 and so on. We'll see humidity is high and then wind is strong. We'll worrying about these values. So this is what we have calculated and we multiplied for all the yeses. So this is play tennis is equal to yes weightage. This is a weighted property. It's 9 by 14. How many times play tennis is yes out of 14 instances? It's 9 times. So it's 9 by 14. Right? So step 3 is we are multiplying all these probabilities for yes multiplied with the weighted probability. It's coming at around 0.00529. Then in the no case, it is coming around 0.02057. So maximum argument is 0.02. If I round it or truncate the digits, I'm taking only first after decimal 2 points. So after decimal is taking 0.00 while it's taking is coming 0.02. So this is higher than this, and higher it means it's no. It is no. There are 2 classes. Huh? This is yes and this is no. So our test instance will go into no class. Play tennis is no. This is the fundamental. Now the question is, we have taken both examples of discrete values. Discrete values are a bit simpler than continuous. In the continuous, it is assumed that the distribution is of Gaussian distribution, normal distribution. Normal distribution, if you remember, we pass the total number of values, instances, then the mean mu and standard deviation. So the Gaussian distribution is like 1 by square root of 2 pi sigma e raised to power minus x minus mu square divided by 2 sigma square. Sigma is nothing but standard deviation. So this is the probability. This is nothing but a probability for every class. We have to find the probability for being a attribute with this value. Instead of the earlier formula, we'll place this formula when the value of attribute is a continuous. It's not discrete. Now the question comes in mind, how do we make the range? If we have continuous value, suppose I'm coming back to this one. Instead of this hot and mild in temperature, instead of this hot and mild, if we have a range, more than 24 is hot, 24 to say 19 is mild, and below 19 is a cool. If we have a range, then we can have the upper and lower limit for range to reach to this value. That's another possibility. Or we can do this. We can do this one. Right? So this is again a big question. People generally ask, how do we use naive-Bayes classifier when the values are continuous? It's not discrete. So look at this. This is a normal distribution. Here we have taxable income is continuous. Refund is discrete. Marital status is discrete. And this is evade is a class. right? So here the taxable income, this first way I told you now, that we can have a range, upper limit, lower limit, and we can make them in a discrete. This is the easiest way. But sometimes it's not advised to take the ranges. We have to directly deal with the continuous value. So this is the formula. This is the formula, Gaussian distribution or normal distribution, one and the same thing. And here, instead of having the discrete yes and no in two values, we can say sample mean is this. Sample mean, how do we calculate? 125 plus 100 plus 70 plus 120 plus 19 divided by 100, divided by 10. These are the 10 values. Huh? So this is coming 110. This is a sample mean. Sample variance we can always calculate, and the income for no income, when this is the question, what is the value being asked in the test case? That is it, 120. So what will be the probability of having this 120 when the class is no? And similarly, we have to calculate it for income is 120 when class is yes, using the formula. So we can check this sample mean. Is this, this sample mean is for no class no. This is no is 120. This is no when 100. This is no 70k. This is no 120. Will not consider this yes. Then we'll come to no. This is 60. Then no 220. And this is no 750. And this will not consider. Got it? So yes cases are 1, 2, 3. Out of 10, yes cases are 3. So 3 will be computed. Mean of 3 will be computed, and mean of 7 will be computed. This is sample mean of no, and this is sample variance of no. Similarly, we have to do it for yes. Got it? So here you can see it using the formula. We have to found it out. This is value for no is 0.0023. And when the class is yes, it is coming 0. This is 10 raised to the power minus 9. This is 10 raised to the power minus 9. Now, the question is, it's obviously 0.0023 is greater than 0. Why is happening? Because this value, the second value, P refund is equal to no when class is yes. Is no instance of this when refund is no. This is the major issue with the name-based classifier, because we are multiplying. If any one of them is 0, it will make whole the thing 0. Right? It's possible that the value of any attribute that is being asked in the test case is not available in the training case. Got it? So that will be 0. If no case is available, that will be 0. And that will make whole the value as a 0, because we are multiplying. This is a major issue with the name-based classifier. So how do we deal it with? So what's happening here? Look at this. This is no. This 0. 0 is nothing but no, married, 60k, and no. And we want to have this class is equal to yes, refund is equal to no, class is equal to yes. This is class is equal to no, something like that. So no case is available of this one, so that's why it's making 0. Now, to understand, in another example, I have removed one instance, and somehow this was the only instance for particular values, and that was contributing in no example. Now this is also making 0 for no. Now both are, instead of this 0.0023, it's becoming 0, and this is also becoming 0. Now the question is, the test case will go in which instance? Because both are 0, right? So this is the major thing that we have to deal with the name-based classifier. So Laplace smoothing is a way. Laplace smoothing. What is this? Laplace smoothing. We add 1. Ultimately, what is this? 0. The values, those who are multiplied, are having numerator and denominator. Denominators are nothing but the instances of that class. Out of 20, 13 were the instances of no class and 7 were the classes of yes class. Right? And denominator is how many times it's appearing. If something is appearing 0 times, none of the case was there, then if we add it, because ultimately what we are doing, we are comparing only, no? Here we are comparing. This we are comparing, this versus this. And we are sending to the instance in a having maximum value. So just like a comparison. So if I divide two values, A is compared by B. If I add something A plus 1 compared by B plus 1, it doesn't make a difference. Right? Or if I say A1 value or A2 value are being compared, A1 is smaller than B1, A1 is smaller than B1. So A1 divided by 10 will be smaller than B1 divided by 10. If I do something the same with denominator and numerator, why do we do it? Because zeros are means they are creating nuisance, zeros. So if I add on something a bit, those that is not making my things 0. In same way, both the classes, all the classes. I am doing the same calculation in all the classes, then my purpose will be solved, making it non-zero. Getting? So look at this. This is a Laplace smoothing. Here, if we have a original is a number of classes, and this is the number of instances in the class. If we have got 2 classes, yes and no, so how many instances are of yes class? How many instances of no class? This is what we have to do. If I got 3 classes, so 3 times I have to check it. 4 times, 4 classes, 4 times. So these are the number of instances of particular class, and IC is the number of instances of that class of that attribute. Attribute 1 is having value yes, then what is the probability of having this one? So if I add something, say 1 in numerator, and I'm doing the same thing with the denominator. Here you can see this is a plus C. Plus C is nothing but the number of classes. Getting? If I add it in the text classification, this is nothing but the distinct key terms in all the documents. Those may be yes class or no class in all the classes. Distinct keywords are used. Somehow, what we do, we are doing the treatment of all the classes the same way, so that we get rid of having the 0. 0 was creating nuisance because it was making everything 0. So instead of 0, if I say 0.0001, that's good. That's better than 0, right? So the treatment, that's the Laplace smoothing, is adding something in the numerator and adding something in the denominator in all the cases. Same way, right? Similarly, there's another smoothing, that is M estimate. Generally, in text classification, we use Laplace smoothing. Getting? So this is same. This is Laplace smoothing. Here, this is +1 has been added, and T is a number of unique words. That is a distinct keywords in all the classes. Suppose I have got 2 classes, sentiment classes. I'm talking about sentiment classification, positive and negative. So first I have to check all the documents, find all the distinct or unique keywords. That's my vocabulary size. So I'll be adding this vocabulary size in the denominator of all the estimations. Got it? Why do we do it? To overcome the issue with the 0. 0, it's nothing but the instance is not found in any class. Getting? So again, a simple example of text classification with naive-based classifier. My question is, in which class it will go? There are two classes, sports and not sports, and these are the instances. So here we have a great game. These are the three keywords, distinct keywords. The election was over. Very clean match. A is not a distinct because already appeared, so we'll not count it. Clean is already there, but is new. Forgettable is new. Game is already there. It is new. Was there already. Was there already. Close is new, and election. This is how we have to count all the unique words. That's my vocabulary size. I'm counting it from sports and non-sports, both the labels. Got it? Now, featuring. This is known as a feature engineering or feature selection. The bag of words that is use word frequency without considering order. So here we have to find what is the weighted probability of a very close game. This is my instance. My question is, if I send an instance a very close game, in which label it will go, either in a sports or non-sports, right? So I'm finding P of a very close game for sports and for non-sports. Both the probabilities I'll find and see which one is higher. So the probability of A, probability of very, probability of close, and probability of game. Now, probability of A when the label is sports, probability of very when the label is sports, probability of close when the label is sports, probability of game when the label is sports. What is the value of this probability of A when the label is sports? So here, when this is sports, probability A, yes, it is there. Probability A is not there. Sports is there. Twice it appeared. No? Probability of A. How many times it appeared when the tag was sports? Twice. How many instances were there? 5. Sports were 3 times. So it's like 2 by 3. It's a 2 by 3. 2 by 3. And this is very sports, close sports, and game sports. And same thing we'll do with the non-sports. Got it? So close doesn't appear in sentence of sports. Close. The close is there in the test case. Yahan pe hai, this is close. But in sports, is there any close? In sports, no. In this close, no. In this sports, close, no. So it will make 0. Everything it will make 0 because close never appeared in the sports category. So which will make our product 0. That's the problem. It is there in the non-sports, close. It is not there in the non-sports. Yes, it is there. So basically, using the naive-based classifier, it is very much visible that this instance, a very close game, will go to non-sports. Getting? But sometimes it's not true. This is inaccurate classification. So to get rid of the 0 issue, what we'll do Laplace smoothing. I hope I'm making some sense. We'll add 1 or in general constant k. Sometimes it's not possible to add 1. We can have some numbers, say 5, 6, 7, whatever. So it's for same. It's for same for every class. For simplicity, it's easy to add 1 because calculation point of view. So what we'll do in our case, a great, very, over, it. This is my vocabulary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. 14 is size of the vocabulary. So in my Laplace, what I'll do? I'll add 1 in numerator and 13. It was 13? Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in denominator, the 14 will be added. So let's look. This is my test case, a very close game. I'll find the probability of this A in sports as well as in non-sports. Good, because attributes are, there are attributes A very enclosed. All the words are attributes. So A appeared how many times in a sports? I counted twice. And how many? What was the vocabulary when it was sports? How did we compute it? 11. Look at this. 11. Sports में क्या था? ये है sports 1, 2, 3. This is simplest example. So this is 1, 2, 3, 4, 5, 6, 7. 7 आ चुका है already. 8 आ चुका है. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here we are not having the uniqueness. We are counting it because term frequency is mattering here. How many times a word is appearing in sports, that is adding to the value. The total number of vocabulary not distinct is 11. What's happening in non-sports is 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we are saying this is 11 and size of the vocabulary was 14. So I have added for Laplace smoothing. Every time I have added 1. It doesn't matter that is 0 or not. We are doing for everyone. Close was 0 only, no? But we are doing this treatment for everything. So instead of 2, it's now 2 plus 1. Instead of 11, it's 11 plus 14. Right? The same way we have done it for all the words. Now we have to do it for the non-sports. So here look at this very is not available in non-sports, and that will make our things 0. So instead of 0, what I have done, I have added 1 using the addition of 1 in the numerator, and what has been added in denominator, that is 14. 14 is for both the labels. Now when we compute it, earlier it was 0 because of this clause. Now it's 0.000276. So something is better than 0. Here we have reached to 0.0000. How many zeros? Here 4 zeros, here 5 zeros. Which is higher? Earlier it was going non-sports. Not going in non-sports. 0, 0. Both were 0, 0. Because very यहाँ पे 0 था ना. So it was 0 also, it was 0. So now it's 0.000276 and it is 0.0000572, which is higher, this one. So drastic change. We have reached some conclusion. That is, my instance will go in a sports, right? Because you can see it very well that game and sports are synonyms somehow. And sports related things are going in sports and non-sports related things are going in non-sports. So that way it's easy to understand that it should go in sports, but just because of clause, it was making it 0. That was the issue. And this is how we handled it with the Laplace. Similarly, we have vector space. Veena ji, do you have any question? Or by mistake, you have raised your hand? Please write on chat. Okay, I'll answer your question if you have. So the second way of text classification is vector space. So far you must have seen vector space is every document is turned into vector. Vector is like a single dimension array. And the contents of array is nothing but the words or the terms. Right? So documents of the same class form a contiguous region of space. If I draw a graph, then the similar features, those are making a cluster. It means they are going into one class and remaining in the other class if you have only two classes. Right. So in vector space classification, training set corresponds to a labeled set of points, and we have to learn a class. So look at this. If I draw a vector, these are the features. And I have converted these terms into some values so that I can draw it. Getting it? So somehow, if I have got three classes, government, science, and arts, this is what exactly we want. I have given a different colors of these sticks. So you can see in this vector space, these features, those are going into science, say friction, this is experiment, or something, and this is say arts, black ones, and this is red ones are government. Depending on the feature, we have converted into vector, and vectors are drawn. This is what we want to visualize, but it's difficult that way. Now, the question is, if this document comes in, this is a different in shape, that's a rectangle. How do we class? Where should I send? Should I send it to the government? Should I send it to science? Everything depends on the similarity. So how do we find the similarity? And from where? Should I find this similarity? Should I get this similarity? Should I get this similarity? Or should I get this similarity? Or should? Because all are close. Right? So this is the question. In which class we should send it? So this is, you must have seen in various algorithms so far, that we have some demarcation, some boundaries. Those make our classes in different clusters, different sections, different classes. So using these boundaries, we can see it very well that it will go into government class. Now the question is how to find the good separators, good boundaries. Got it? If you have done SVM in SVM or any other classifier in data mining, it's easy to handle it because we can apply any kind of similarity distance measure. Maybe some Euclidean distance, Manhattan distance, cosine similarity, lots of ways. It depends on the application, which one is to be chosen. Right? So now the question is, how do we do it? Before we proceed further with the vector space, there are two terms. Term frequency and inverse document frequency are to be studied first. Inverse document frequency may be new term for you. That is making some non-popular words important. There are some terms, those are frequently coming. If the terms are coming in all the documents, those are instances, then those terms are not very useful, very important. We can discard it. But some are coming many times in some documents, say 70% documents having the document, these terms, that too with some number. But 30% documents are not having those documents. Those are important ones. They are making sense. Inverse document frequency means some terms, those are very rare. But of course, they are contributing towards labels or classification. So this is a trade-off. Getting the importance, those are popular, making sense, and those are very rare and making sense. So we are combining them. So inverse document frequency, as the name says, we are having the documents. IDF is nothing but the log we use for the computational purpose, damping the effect. If we have the big numbers, and capital N is nothing but the corpus collection. If I say I have got 1 lakh documents, and DF is nothing but the document frequency. It means number of documents that containing the term. If this is lesser number, suppose एक document में एक term आया, it means that term is very useful. We are making sense. We are getting some sense out of it. Right? So it is in denominator. So it's lesser, it means it's a higher value. And why do we do log? Log is just for the computational purpose, dampening the effect of big numbers. Term TF is nothing but term frequency, how many times a term is appearing in the document. Inverse document frequency is the inverse of the document frequency. So we are having a trade-off. We are making the important without log or without something, without inverse, and those are appearing rare. We are doing it inverse so that they get the impact. So this is term frequency into inverse document frequency into I. This is into. This is known as a TF-IDF. Very important in IR community. And I am relating your IR with NLP. NLP in the terms of text classification. So look at this. We have this document. This is again a vector. Vector is a collection of terms, right? So first of all, we have to make a term document matrix. So in this side, above side, we keep all the documents. In the below side, we take all the terms. Then we say this term is appearing in this document how many times? That is a term document collection. So this is in one document, suppose 3 terms are coming and remaining are 0. So we'll say 0, 0, 0, 0, and last 3 terms are 1, 1, 1. That's a vector. Similarly, for the term document 2, it has only 2 terms. First 2 terms are there and remaining are 0. So it will be 1, 1, remaining are 0. That's a vector. So we can represent the number of terms are nothing but the dimensions. So we can represent these two terms in n dimensions. If I got 2 terms x and y, I can say first document is having first term and second is 0. This is 1, 0, and second is opposite 0, 1. So I can represent in terms of graphs. So now the question is third document. The third document will go in which class? So documents can be considered here as a classes. And the question is, the objective is, we need to send this third document, that's query here, in the particular class. So this is how vector space model is being used for the text classification. Document 1 and document 2 represent 3 points in the vector space here in this example. And we have to compare the query of the third document, that is our test case, in which document, in which class it will go. So there's a similarity. Just I told you, there are many ways to find the similarity. First one is a Manhattan. Second is a Euclidean. Third is a cosine similarity, very, very popular. Cosine similarity says that weight of first document into dot product into weight of second document divided by all the terms square root of terms into square root of square of second document's terms. Second means the query here. So we need to find the cosine similarity between document 1 and query, and we have to find the cosine similarity between document 2 and query. And the higher one, the similarity, it means they are overlapping with each other. The lines, the red line here, this is red line, is overlapping with this document. It means similar. The cosine angle is 0. Cosine angle is 0. It means they are similar. Cosine 0 is nothing but 1. Cosine 90 is nothing but 0. So if they are similar, it means cosine is angle is 0. It means they are reaching to similar one. Value is higher. So this is the similarity measure, cosine similarity. First, we have to get the documents, and this is search query is nothing but the search instance, search document or document to be classified. First, we have to pre-process. As I told you, the important thing is a feature selection. So in case of text classification, we can remove punctuations like comma, colon. One term is normalization. If I say person's name, person apostrophe s. So if person apostrophe s is nothing but only person is enough for us. So apostrophe S is to be removed. That is known as a normalization. Stop words, there are some words, those are very important part of the sentence or document, but not making sense in terms of classification. So these are around 487 words. Those can be removed. Those are known as most frequent, means not contributing to classification. So same method and same behavior we do with the documents as well as the test document. Then to lower is a function which makes all the words into lowercase. Why do we do it? Because if I say RAM, R-A-M, capital R-A-M, that's a noun. If I say R-A-M, that's a RAM. So here in this game, both will be treated as the same. So this is the main issue with the NLP. The RAM, that is the name of the person, and RAM, that's the RAM. Both are taken as the same. So we have to find in which context it has been set, right? So that's the issue with the NLP. So there are many ways to handle it. We'll not deal with this in this lecture. So again, once the processing has been done on documents as well as in the test document, we get a term document matrix. Term document matrix, it means a term in appearing in which document. All the documents have are given a number 1, 2, 3, and terms are written. Every term is to be checked in every document. It becomes a sparse matrix. Sometimes we say 0 and 1, term is appearing in the document or not appearing. And second way, we say term frequency, how many times a term is coming in the document. And apart from that, we have other things as well in the term document, at what position is coming, in which order it is coming. So later we keep on digging it. So for now, it is simple. We are taking term document terms. The term is appearing in the document. Terms are indexed, documents are indexed. We can find it out. A term is appearing in the document in terms of 0 and 1. That is term document IDF, term DFI, queries TF IDF. Then we have to calculate cosine similarity. And the similar documents are kept in a same class, and non-similar or dissimilar documents are kept in a different class or a cluster. So again, we have to sort and select top K relevant documents with large cosine similarity values. Large similarity means 0. So cosine similar values are from 0 to 1, right? So 1 is the highest similar and 0 is the lowest similar. Got it? The same thing we do with the IR. IR is the information retrieval. Search engine is using it. Search engines are using it, right? This is very popular method. Now, word embedding, I'm relating with the text classification with NLP. That's why I have taken it. The word embedding is like word to vec. Some word embeddings models are word to vec. Google has given it word to vec. Globe is given by Stanford, and Fastest is given by Facebook. These are the word embeddings already given. We have some standard vocabulary and they have been converted into Word document. They have their own vectors. So we can directly use word to vec. So Python has got library for that. We can directly use it. We don't have to document it. For example, if you have fruits like apple, banana, mango, so they are placed close. They have the similar value so that we can read it. Books from fruits are different. Book is different from fruit. So they are placed far from these words. So word embeddings will create a vector of fruits which will be placed far away from vector representation of the book. Got it? So this is about the word embeddings. This is very widely used in NLP. So you can see in terms of vector space model. So word to vec is a technique model to produce word embeddings for better word representation. I hope this has been covered in first and second lecture, so I can skip it from here. This is a globe embedding given by Stanford University. So now the third classifier is Roorkee classifier. Roorkee. It may be new for you. So as we have seen, that everything is converted into vector. Vector is nothing but the values of term. It may be 0, 1, it may be term frequency, it may be TF, IDF. Sometimes the vectors are keeping TF, IDF for every term. So this A is nothing but a sigma. Sigma, please make it sigma. Centroid is nothing but like an average. All the documents, those are related, are kept together and divided by the number of documents. Modulus of DC is nothing but the number of documents. This A is nothing but a summation. Please make it summation. Where DC is the set of documents that belong to class C and VD is the vector space representation of the D. D may be the vector representation, may be word embedding that has been given by the standard vendors like Google and Word2Vec, and we can calculate our own. First way is a term vector, 0, 1. A term is appearing in the document, that's a vector space. Third thing, we can take TF, term frequency. Fourth, we can take TF, IDF. TF, IDF is nothing but the weights of the terms to represent the vector. So the centroid will be in general not be a unit vector, even then inputs are unit vector. Why it's not so? Because we are dividing. अगर हमने लिखा 1 0 1 0, the centroid may be 0.5 because we are getting the average. The Roorkee algorithm, Roorkee classification is very well used in IR. It is IR in terms of relevance feedback. Relevance feedback is nothing but getting the documents those are relevant to the query or a person who has fired the query in terms of the relevant documents and non-relevant documents. Here the text classification, it's not guaranteeing that classification are consistent with the given training data because it depends on the centroid. And centroid is the value instead of, suppose here if I say, yeah, here if I say this is red line, if you can see it, it means this is a text document, that is a test case. And here we have the positive documents, here we have negative documents. Got it? Instead of document number 2, I have got say 20 documents, those are negative sentiment and these are the positive sentiment. So here only one document you are seeing, so it's easy to have the similarity between the text one. But what if we have say 100 documents? So I'll get the centroid and I'll compare this text document with the centroid one. Similarly, I'll compare this text document with the centroid of all these negatives. That is a Roorkee classifier. I hope you understood. You can ask question. This is what I wanted to show you. So look at these are the documents. Here, these are the different colors. Some of are the red and remaining are the blue. So blue is another class and red is another class, right? And big red is a centroid and bold blue is a centroid, right? So now the question is, this one. So suppose this is our test class, this one. I hope you are seeing my pointer. Yeah. So I'm calculating the distance of this test class with this centroid and this test class with this centroid. Getting it? So which is similar? This test class will go looking at this. This is a lower angle. If we have lower angle, it means more similar. So this test class will go in this class, blue one. This is what is happening in Roorkee. So before I come to the next classifier, there's a term bias and variance. Although I have tried to explain in terms of underfitting and overfitting, these are related with. So bias is nothing but the difference between what we expect to learn and what is actual. What is predicted one and what is actual. The difference between that is a bias. And variance is difference between what we expect to learn and what we learn from the data set. What is expected and what we are getting. This is variance. Getting? So we have to have the trade-off, because we don't want low bias and high bias, and low variance and low high variance. There are 4 terms: low bias, high variance, high bias, and low variance. So these are related with undertraining and underfitting and overfitting. If overfitting is there, it means we have a low bias, means training is done well. When training is done well, it is low bias. And when the testing, there are 2 types of accuracy: test accuracy and low training accuracy. Training accuracy is high. It means we have trained well. Our modifier is working well, but it's not working good for the test cases. Then it's a test accuracy. So it's not possible that high accuracy in both the cases. Sometimes we have to trade off. The chalegas kind of. We can say yes, 90% results is good for me. So 90 is nothing but 100. We want to achieve 100, but we can achieve only 90. So this is a kind of difference. Predicted is this and achieved is this. We wanted to have this, but reached at this. This is the difference. So when this is what happening, then we have to think about the feature reduction. Suppose I've got 100 features total, and it's difficult to handle all these 100. I can reduce to say 10. What are these 10? Out of 100, I have to choose 10. Which 10? So we can select it manually, first thing. And second thing, we keep all the features, but we give the weightage to some of the features. Some features have high probability, high priority, and some features are low priority. So we have a lot of features, each of which contributes a bit to predicting why. This is known as a regularization. That is a theta. So that is basically penalize the large values of features. Instead of reducing the feature, we are keeping all the features together. But some of the features are having, say, one is 100% weightage, some are 0.5, some is 0.1, and so on. Right? That is a regularization. Then summary, representation of text categorization attributes. Representation of the text are usually very high dimensional. Of course, text means all the words are dimension. Attributes. So far we have seen in data mining examples, three features, 4 features. Here I have got, look at this page only, this slide only, how many distinct attributes. Those are the terms: summary, representation of text. These are nothing but the attributes. So it's a high dimensional features. This is the issue with the text classification. So we have high bias algorithms that prevent overfitting should generally work best in the high dimensional space. For most text categorization tasks, there are many relevant features and many irrelevant features. Many relevant fields. So we can't reduce all these so that we may not lose the important thing. If those are relevant, but somehow in the reduction, they are gone away. Or many are irrelevant, we have reduced the feature, but still we kept only irrelevant ones. So it's not like that in the one way it's done. We have to keep doing. We have to keep training and getting the accuracy. Right? So now the question is, which classifier do I use for a given text classification problem? So is there any learning method that is optimal for all text classification problem? No. ऐसा कुछ नहीं है, because there is a trade-off between bias and variance. Bias is low when training is done well. Bias is high when training is done not well. Variance is high when test accuracy is low. Variance is low when test accuracy is high. So because as such there's no answer of it, we have to check it again and again. So what are the factors to be taken into consideration? First is it depends on the training data, how much training data we have. More data is good for accuracy. Because if we have less data, there is always a biasing. It's working well for this, but it's not working well for that. But in case of big training data, it works well. The second is how simple and complex is the problem. Is it a linear or non-linear, having the decision boundaries? So we have seen the example where 3 classes were there. We could see the boundaries. What if we have, say, 100 classes? We can't even see the boundaries. And sometimes boundaries are so complicated, so it's difficult to write the equation. Classifiers or boundaries are nothing but the equations. Equations, it means it depends. If we have x1, x2, x3, these are the data items, then how do we place these values in the equation? The third parameter is how noisy is the data. How noisy? Means, do we have some missing data? Do we have outliers? Do we have skewed data, imbalanced data? The question is this. And the next one is how stable is the problem over time? Sometimes it happens that the problem is good, problem definition is good for today, but may not be good for tomorrow, or it was not good for yesterday. It's time dependent. So somehow in our equation, time is a factor. And for an unstable problem, it's better to use a simple and robust classifier. Right? If we don't have a stable problem, then it's good to use simple and robust classifier. One of them is naive-Bayes classifier. And for IR problems, Roorkee algorithm is good. This is a general observations. Right? So this is all about the text classification. This is my email ID. And quickly, we have 10 minutes to go. Quickly, I'll show you the explanation of ensemble classifier. I have done it for you. I'll share the Jupyter notebook so that you can do it at later. I have done it in Colab. I hope my screen is visible. I have written my Python code in Colab, and my data set is also there. I'll mount the drive. Okay. This is the example of ensemble classifier. So what is this ensemble classifier? Ensemble classifier is assembling of many decision trees because many attributes, choosing which attribute first, how do we decide the boundaries? Suppose I have said temperature is this, it has got 3 values, high, low, normal. So how do we have a decision boundary, and how many rules are there? How many branches of trees are there? So everything depends. So this ensemble classifier is randomly taking the decision trees and ultimately taking the average of all the classifiers. So as you know, we have to import a NumPy library for number applications. Here we have used RE's regular expression for pre-processing the text class. This is an example of text classification. So that is very much needed. For example, I have said this person's salary. So I need person and salary, these two terms, right? So a post of S and S will go away. So first person S will be there. Then I'll check any S or any a single letter word before, after a space and before a space to be removed. That I can do it with regular expression. NLTK is an important library. It's a natural language toolkit, and that has been imported here. sklearn is for dataset. यहाँ पे dataset हमने रखा है. And import, this is again a library. Load file is needed for loading the file. NLTK download stop word. This is This is downloading stop words. I have run it and it's working well. You can see it's downloading package stop words to root NLTK data. Unzipping corpora stopwords.zip. This has been done. Now, I hope it's visible. Someone can say something.
Yes, ma'am.
Okay. So don't worry, I'll share this one. So next time I'm putting NLTK down. WordNet has been used, although I'm just showing how do we do it. I haven't used it perfectly. And apart from WordNet has again got some sub-libraries. You can say sub-libraries. So I haven't used it, but we can use it for NLP purpose. There's a possibility that you have done it already. So here the data set is again in the collab, means drive. So first I need to mount the drive. This is what is being done. Is saying connect to Google Drive. I have to say yes, and then I have to give the permission. This is my drive name, and then I have to allow it. Just allow. It's mounted already. Then I have taken movie dataset. It has got two classes, positive and negative sentence, positive and negative sentiment, two classes only. So this is, I'm loading from my drive. Here I have kept my dataset. This is text class, my drive. It has got text classification and text sentiment tokens. I have converted this movie dataset into two parts. X is my training data, Y is my test data. Movie data, comma, movie data.target. So movie data.target will go into X, Y, and movie data.data will go into X. This is the function. I hope it's working well for you if you're doing it. Otherwise, you can do it later. I'll share the Jupyter notebook. We'll do it on Canvas. We'll keep it on Canvas. So this is the basic example of text classification using random classifier. It's going on. So we have to wait for 2-3 minutes more. I'll request Bhaskar sir to please delay by 15 minutes of your second session so that they can have a break.
Sure, ma'am. You continue.
Okay, thank you. I'm not sure why it's taking time, maybe just because of internet. So timing, I can explain that first it will mount drive. Means your Jupyter notebook is your code and data set. They are getting the data set in your frame data. Means data is being taken into this drive. drive is already there, data is already there in the drive. They are getting the data, loading the file. The next one is I hope it will be over in few seconds. Earlier it took 4 minutes for me. It's 2 minutes are over because data size is big, so it's taking time. So what I mean to say that we have to mount the drive. Permission has been given, and the data, the movie data, will be loaded into X and Y. Y is your test data, X will be your training data.
Hello, madam.
Yes, please.
May I ask question? Actually, in
Yes, sir.
what to make, it is, we say it is 300 dimension. So
Yes.
what can be that 300 value, means what it signifies?
Means there are words, those are having some meaning, some values. So as I'm saying, suppose I have a say 10 documents and they have 100 terms. So every term is to be mapped with the document. This term is there in the document, say 1. This term is there, not there in the this second document is 0. This is nothing but the 0 and 1's value. So if there are 300 words, instead of having 0 and 1, this is a significance. Those are similar in meaning will be having the similar values. You can go and check the word to vec this one. You just Google it and they will show you the values. This is done by, word to vec is a word embedding and well-known technique. So
Yes.
after having so many of research, the similar values are kept together. Just I've taken the example of fruit. Fruits are different from books, or fruits are different from laptop. So how do we make them dissimilar? Basically, there's a game of the numbers, and those are similar, having the similar values, so that we can keep them together. And those are having dissimilar values, dissimilar meaning, they have the different values. So
We
everything
can get those values. We can
yes,
get that
we can check,
values.
not get that, but we can check them, so that our purpose. Even we can have the word to vec can be extended by you. You can use them because this is not fixed. Lots of documents are there. It's not that complete that we can depend on it. It depends on our application. How do we modify it? Similarly, there are lots of other word to vec word embedding techniques. I'm doing it once again. I'm not sure what's happening. 4 minutes are already there. It's a question of, I think it's a question of I'm doing it once again. Okay, so I'm skipping it for the sake of time. So this will be done. I have done it before, just before I started my this one class. So next one is I'll explain the things I have done it. Stammer. There's a term stamming and lemmatization in NLP, and in terms of pre-processing. Every word, suppose I say my document has got implementation, the term implementation, while in the test case it is implement. So will they be similar, implementation and implement? Or I say good, better, best. So how do we make them related? So lemmatizer or stammer, lemmatization or stamming. There are two terms, they reach to the base word or a root word. If I say implemented, implementation, implementing, implements, all these are nothing but the forms of word, root word, implement. So in every case, we have to reach to the base word so that we can find the similarity. Got it? This is the one thing that is used for the pre-processing. Similarly, we have to remove the special characters, because special characters doesn't make any sense in terms of the classification. So we can remove it. Similarly, we can remove single characters. As I told you that currencies, if I have currency, then it will be currency. If I have better, it will be good, right? If I have best, it will be good. That way we can change it. So there's a bit difference between lemmatization and stamming. It depends on the application, what we want. NLP has a big thing about it. You must have done it or you will be doing it. Similarly, we have other processing. Something is starting from a character. Remove single character from a start, can be removed. And after a word, that's a single word, S or A or say T, anyhow it came T or N. So we can always remove it. Then removing prefixing also everything is done by RE. RE is nothing but the regular expression. Then we have lower. Everything is converted into lower, and then split. If we have two words together, then those are being splitted. So all these are needed for the pre-processing. So anyhow, I'm not able to show you. It's working well, but I'll share you. Just click it. It will be working good. So next is term frequency is calculated. Term frequency is nothing but the number of occurrences of word in a document and total words in the document. That is known as a normalization. If we have a big document or a small document, in both the documents, big and small, the term is coming say 10 times, which has a weightage, the small one. That's why we are doing it. We are dividing it by the total number of words in the document so that they get the equal weightage. Similarly, we are calculating inverse document frequency that I have seen it. So this processing is done for all the classifiers in the text classification. In the text classification, there are a number of classification. These terms are needed for all the classifiers, right? So here we are converting. This is again part of this. Now I'm using ensemble classifier. This is random forest classifier. This is one of the good classifier for text classification. Here you are seeing two parameters. One is n number of estimators that has been taken here for sake of simplicity 1000. It may be anything. So it depends the number of text documents we have with the training. And random state is nothing but a seed value. When we do random number generation, the seed number is needed. Here I have taken 0. You can take anything, right? If we keep on changing the number of estimators, maybe 10, maybe 100, maybe 1000, or number of seeds say 1 or 2 or 3, it means we are going to get different results. Then take this classifier has got two values. This classifier has received using this one has got two values, X training and Y training. So Y training is nothing but the values, and we have to calculate X is a training data set, and we have to fit it for Y training, and this Y predicted is a class. Here we are X training, we are using it for text test. We can bifurcate this full training data into one, training and testing. Training and testing. Generally, we keep it for 70 and 30. Same data set. We can have 70 and 30. We can have 18, 20. And every time we do it, and ultimately we get the average. Right? So, I'm sorry, I'm not able to show it. Otherwise, we could have seen it. Then we have to use it, the ensemble library that is there in the sklearn, right? And this is training text classification model and predicted sentiment. This I've done it. And we have to check it, what we have done is good or not. So how do we check it? With the test measures. We have confusion matrix. Confusion matrix has got true positives, false positives, true negatives, and false negatives. So true positives are those are correctly classified. And false negatives, true positives, true positives, TP, false positives, those are falsely found positive. False negatives, those are not negatives, but made negatives. And true negatives are, those are in negative class and gone into negative class only. So we are worrying about we need to increase the true positives. So here, this is a confusion matrix. Out of 402, this is 402 instances. Out of 402, these were the true positives are 171. Those were found positive and they were positive. 34 were falsely found positive. They were not positive. And similarly, there are 46 are false negative and these are the true negatives. It means they were negative and found it in negative. So this is how we can find our accuracy. It is 171 plus 151 divided by 402. This is 80%. So precision, recall, F1 score and support. These are the measures in TICS classification. Precision, it means we found the true positives divided by total number of positives. Kitne hone chahiye the, and this is what we have received. So this is the formula for all these things, and we can always have an average. This class, this 0 is a negative class and 1 is a positive class. There are two classes. If we have more than two classes, we can write it here and get the precision recall. Basically, this is meant for the binary classification. Got it? Micro average and weighted average is nothing but we can give the weightage. 2, 0 and 1, the classes. Here equal weightage has been given. That's why macro average and weighted average are same. This is again, we can find the precision performance matrix. Precision, I'll share the Jupyter notebook so that you can run it. And in case of need, you can see the explanation that is available on this site. This is like a GitHub site. They have given the data set as well as the code. So I have run it my own. I have taken data set according to my need. I have made it a bit shorter so that I can show it to you. But anyhow, I couldn't run it. That's enough from my side. If you have any question, please ask. I would be happy to answer the questions.
Hello, madam.
Yes, please.
So features actually is the distinct words which we are using in a particular data set.
Yes,
But features are also used to refer some property kind of thing, attribute of certain thing.
Yes.
So
Yes,
why these two terms are not taken separately? Means we call in general features all the time.
Yeah. In general, if we start from data mining, features, attributes, behavior, properties, they are nothing. They are the just means to differentiate the two instances. If I say there are two students in my class, they have student ID, student name. These student ID, student name, and other things are nothing but the behavior of those students. Or we can say these are the properties, or we can say these are the attributes. Right? So same way in the text classification, because we don't have the instances, we have the text, we have the documents. And document is nothing but the collection of words or terms. Right? If a term, sometimes words and terms are taken as same, sometimes words and terms are like a term. If the word is appearing uniquely, then it becomes terms. For my convenience, I take word and term same. So if I say stop words removal. So these are the words, those are not making sense because these are not terms. I hope I made some sense.
Yes. Thank you.
I would happy to answer if anyone is asking. Even you can write a mail because I have taken it very simple. I have not taken my research papers. My students have worked a lot in sentiment analysis as well. You can see the papers from Google Scholar. And in case of need, you can query as well.
Ma'am, could you please share that Jupyter notebook to us?
Yes, sure. I'll be there. I'll be doing it on Canvas. Please try to run it. It's very simple.
No, madam, you can share it in the chat box here, so we can immediately copy and paste and run it. Link if you can give in this chat box.
Yeah. It will take time to share because I'm minimizing it. Chat box kahan hai? I'm not seeing chat box.
Hello, ma'am, am I audible?
Yes, Swati, you are audible.
Yeah, ma'am, I have one query. Whenever we evaluate any classification algorithm, so we have so many measures with which we can evaluate the algorithm, like recall, precision, accuracy, F1 score, so many are there. So is there any criteria on what basis we are calculating these parameter? Means my question is like which parameter we should use for evaluation?
Actually, no as such fix. As I told you, which classifier we should choose. There's no as such answer. This is good for that. So it depends on application. Precision we use when we have the retrieved documents. If I talk in terms of information retrieval, they are retrieved documents, relevant retrieved, non-relevant retrieved. So if we retrieve the documents, those are the higher ranks. If I retrieve a document that at the first position, that's good enough for me. The second case, in case of recall, we don't worry about the ranking. We worry about we worry about the ranking. In the recall, we want retrieved are placed at the ranks, first, second, third place. जितना जल्दी अच्छा मिलेगा उतना अच्छा होगा. While in case of precision, we are saying, suppose I have fixed first 10 documents. So they may be anywhere in the first. While in the case of recall, we want only 2 documents, but should be at the first or second place. So it depends. It depends what we want exactly. So that's why we are taking all these together. We want this also, this also, this also. We have to have a trade-off. So
for classification,
ideally recall and precision are 0 to 1.
Yeah.
So when the recall is going down, precision is up. And when precision is up, recall is going down.
Correct.
So ideally, both should be 1-1. That's not possible. So that's why F1 score came. F1 score is a harmonic mean of precision and recall.
Yes.
Right? So instead of taking precision and recall, we can go for harmonic mean. So that's a trade-off between these two. So in general, for my students, I ask them to use F score. And again, we can change the weightage of precision recall, that is using F measure. Sometimes we keep equal weightage, sometimes we can change the weightage. So it depends on the application. Suppose I am going for the medical emergency cases, medical images, right? Medical images, what we want? We want less numbers to be retrieved, but whatever we get should be accurate enough. We can't afford to have the non-relevant results. That time we use recall, right? While in case of other things, we want everything should be there, but maybe piche aa jaye, but we need everything is to be done.
Yes.
Then we need precision. So no such answer that yes, in this case, this will be good, or this will be, we have to do it, means researching again and again. So that's why we need experts or domain experts. Those they can say, yes, it's good, it's not good. We cannot rely on the numeric values. We have to check with the If the applications are with the society, we have to check it manually. What we are getting are good or not.
Okay, ma'am. Thank you.
Yes, please. Any other question?
Ma'am, please
Sorry,
share the
sorry,
link
ma'am.
to us.
I'm not able to see chat here right now. I have to create a link, and definitely I'll do it. Ma'am, Shriparna ma'am has joined, so I have to leave it. Thanks for joining, ma'am. I'm going. Thank you.
Okay, thank you, ma'am.
Sorry for
Thank you,
sorry for late.
thank you, Sriparna, for
Thank you, ma'am.
joining. So, Sriparna, can we take a 5-minute break? Because
Yes. Fine.
last ma'am was continuing till now. So let us have
Sure.
a break. So participants, we will start at say it's now 6:20. So we'll start at 6:25.
Sure. No issue.
Okay.
Okay, bye.
Suparna, are you there?
Yes.
What is the name you have logged in?
Webex 7. Webex 7.
Webex 7.
Yeah, I don't know why it was there.
You have to be made presenter, no? Otherwise you cannot share.
Yeah, Webex 7. But I have that power. I have, now I am a presenter. Yes.
Oh, you are presenter.
Yeah.
Sir, are you there?
Yes, yes,
I think we should start.
yes. Dr. Sriparna,
Yes.
can now start.
Okay. Yeah, so today we'll be giving you a demo. So basically, how to develop the summarization techniques. Like I already discussed about the summarization systems in my past lecture. So today, basically there will be a demo. Like we will show you how to develop the summarization system. Especially how can we apply multi-objective optimization techniques for solving the summarization problems. So, but before that, in the last class, I was not able to cover a topic, which is basically called the multimodal summarization. So I just would like to discuss some few slides on that, and then one of my student will show you a kind of a demo. So the thing is that what do you mean by what is a multimodality? Because I told you that multimodal summarization is a very important concept. So our experience of the world is basically multimodal, because you know that whenever suppose you have to take a decision about an object, we used to see the object, we used to hear the sound, feel the texture, smell odors, and taste flavors, and then we used to come up with a decision. So multimodal learning basically collects data from various sensors and such as either text, audio, or video, and then we used to take a decision. So basically, in many cases, you know that multimodal signal is available. Like when we are tweeting in Twitter, we are not only typing in text, but we often post some images. In social media platforms, when we are posting, we often use apart from writing something, we are also posting some images or the videos, etc. So basically, multimodal information is abundant, and there are many places where the multimodal information are available. So there must be a way to build models that incorporated multiple types of there is a basically a way to incorporate multiple data types, text and images at the same time, called the multimodal information processing. So basically, this is the so in multimodal summarization, we are basically considering multiple information sources. We are not only relying on the text. Like in the last lecture, what I have discussed was the text summarization. So there was only one modality, which was the textual modality, and we were generating summary based on the textual modality. But now in this multimodal summarization, we also have to consider the other modality information. Like we can either consider the image, or we can consider the video or the audio, and we can basically generate a summary. The multimodal information can help improve the overall summarization process, as it is much closer to the multi-view cognition that human beings possess. And there is also another aspect that sometimes maybe it is very difficult to express everything in text. So maybe sometimes we can express something in text, and maybe images can give us better clue. Like some concepts can be better described using image. So that is another motivation of doing multimodal summarization. So like concepts like freedom, affection are difficult to describe using images, whereas describing what a piano looks like is quite easy to describe using image. So basically, some concepts are easy to be described using image, and some concepts are easy to be described using text. So large majority of platforms like newspaper, social media, blog post have introduced the provision of including information in multimodal format. Yeah, Vivek, that is the plan. So we will show you some basically some products, not product, but we will show you some how we are developing the summarization systems, and some data sets also we will show you. So just I would like to tell you about this multimodal summarization. So, you know, multimodal summarization is nowadays becoming very popular. And you can see in recent years, there are many papers on multimodal summarization. So basically multimodal summarization is described like this, that we have a set of text documents, we have a set of images, we have a set of videos, and now basically we are applying some summarization technique, and then we are selecting some text as a text summary, some images in the image summary, and a video in the video summary. So in the input side, we have a text documents, we have the set of images, we have a set of videos, and in the output, we are generating some text summary, image summary, and the video summary. So this is basically the text, image, video summarization system. So for this dataset is basically, you know, there was a dataset available. If you see this paper, this multimodal summarization for asynchronous collection of text, image, audio, and video. So in this paper, this Zhu et al, they basically they developed a dataset. So this dataset is containing 25 topics, and each topic is having 20 text documents per topic, 3 to 9 images per topic, 3 to 8 videos per topic, and 3 text references per topic. So there are 20 text documents per topic. There are some images per topic, some videos per topic, and some references per topic. So what we did, so in this dataset, in the input side, there were multimodal information. Like you can see the video, image, and the text descriptions were there in the input side. But in the output side, you can see the output side, image, video, and text were not there. The only text was there, image and video were not there. So basically what we have done now, we have now added some image and the video information in the output also. So this multimodal summarization is now producing not only text summary, but also image summary and the video summary. That is the thing, that multimodal summarization is considering input, text input, image input, and the video input, and then it is producing a text summary, image summary, and the video summary. So we proposed an approach which is using a optimization technique which is called the integer linear programming. So you can see this is our overall architecture. So you can see that in the input side we have the documents, we have the images, we have the videos. Now from the videos we are generating the transcript as well as we are extracting the keyframes. So from the videos, we are extracting the keyframes, and we also have the, you know, audio signals. Audio signals are translated into speech transcripts, and these speech transcripts are added to the, you know, the document set. So the document set is having the speech transcript as well as the multiple documents. And in the image side, we have the images as well as the keyframes which are extracted from the videos. So there we have the text set and we have the image set. And then you can see that we are applying the joint integer linear programming framework. And by using the integer linear programming framework, we are generating a text summary, and we are also selecting top K images in the image summary. And now there is a post-processing technique. So by using these top K images, we are basically selecting some additional images to be added in the image summary, and we are also selecting an important video to be added in the final summary. So the final summary is having text summary consisting of multiple sentences, some images in the image summary, and one video in the video summary. Basically, this is the overall proposed architecture. You can see that in input side we have text, images, and the videos. And now videos are basically separated into audio signals and the frames. So key frames are basically images, and those are added to the image set. And then audio will be translated into speech transcripts, and those speech transcripts will be added to the document set. We are having text set and the image set. Then we are applying the joint integer linear programming framework, and then we are basically, you know, we are extracting some text summary as well as the some top K images. And now based on this top K images, we are applying some post processing, and then we are adding some more images in the image summary, and we are also carefully selecting a particular video for the video summary. So here you can see that we have applied the integer linear programming. So here decision variables are the variables whose values are to be set to the corresponding solutions. The objective function whose value is either to be maximized or minimized to find the optimal solution. We have a set of constants as well. So basically you can see that now what are the variables here. So we have three different matrices: text matrix, image matrix, and the cross modal matrix. So the text matrix is a size of n by n. So where n is the number of sentences in the data set and p is the number of images. So we have a text matrix, we have an image matrix, and we have a cross modal matrix. Cross modal matrix is of size n into p. N into n is the number of sentences and p is the number of images. So MIIX is basically when sentence I or the image I is selected as an exemplar. So basically, you know that if the basically we are applying clustering. We are trying to cluster the sentences and also we are trying to cluster the images. So basically, MII will be equal to 1 if suppose the sentence SI or the image I is selected as an exemplar or not. And MIJ means that if XI votes for XJ as its exemplar. So basically, if suppose there are two clusters, ith cluster and jth cluster, if ith cluster vote for the jth cluster, then MIJ will be equal to 1. And MIJ see if there is a threshold value of correlation between SI and II. So this is our objective function. So we are, it is a single objective function because integer linear programming can only solve the single objective function. So we have the saliency over text modality, saliency over image modality, and the cross correlation, cross modal correspondence. So what is saliency? So saliency is nothing but you can say that saliency is nothing but this one that we are computing the cosine similarity between the item and all the points which are in that particular cluster. So G item I is basically consisting of all the points which belong to that particular cluster. So we are computing the similar cosine similarity between the item I and all the points which belong to that particular cluster. So we are computing this similarity. Basically, it is inter-cluster similarity, and we are trying to minimize this, maximize this inter-cluster similarity. So this is the cosine similarity between all the points with respect to the cluster center. And basically, we are computing the saliency with respect to the text modality, saliency with respect to the image modality, and also the cross correlation model saliency. So cross modal saliency is basically the cosine similarity between sentence and the image. So we are computing the cosine similarity between the sentences and the images. So we are also trying to make the cluster centers obtained by the text modality and the cluster centers obtained by the image modality similar. That's why this cross correlation, this M cross based saliency is introduced. So we have this is a weighted sum. You can see we are having the textual saliency, image saliency, and the cross modal saliency, and then we are computing this. This is the weighted version. We are maximizing this. So what is the joint integer linear programming framework? So you can see that all the matrices are binary. So these are the constants. So either they can take 1 or 0. Diagonals basically represent the cluster centers. So in the two matrices, if the diagonals are 1, that represents the cluster centers. And there must be exactly k txt number of clusters in the text space and k image number of clusters in the image space. Then an entity could be either cluster center or it could be a part of a single cluster. We are not considering the overlapping clusters. And a particular cluster will be formed if it has a cluster center. So now after basically you can see that we are what we are doing. So this is the integer linear programming. After integer linear programming, we are generating a text summary and we are also selecting some images as the image summary. Now we are applying some post-processing technique. So what is the post-processing? So basically you can see that text summary and the top M images from the image summary are given. And now we are selecting non-keyframe images. So other than these images, select those images who have cosine similarity between alpha to beta. So basically we are here selecting some non-keyframe images. And basically we are adding some images in the image summary. And also we are adding a video as the video summary. So each video is given a score, which is a combination of visual score and the verbal score. So visual score is computed with respect to the similarity between the frames and all the frames which are in the summary. So this visual similarity is computed by the cosine similarity between the frames which are in the video and all the key frames. And the verbal score is also calculated with respect to the, with respect to the basically speech transcripts. So we are correcting all the sentences in the speech transcript, and we have the text summary. So it is the cosine similarity between the speech transcript and the text summary. And then each video is basically having a combination of visual score and the verbal score. And you can see these are the results. So the last column, last row is for our proposed approach. And we have completed RUSE 1, RUSE 2, and RUSE L scores. You can see for RUSE 2 and RUSE L, we are able to outperform all the baselines. So for the video also, we are getting almost 44% accuracy. So then we have also, like as I mentioned earlier, so we have also proposed a multi-objective optimization based approach for solving this, multimodal summarization problem. So multi-objective optimization I have already introduced in the last. Yeah, so multi-objective optimization is already introduced in the last my lecture. So basically, multi-objective optimization deals with optimization of more than one conflicting objective functions. So I mentioned that if you suppose want to purchase a car, so there are many conflicting objectives like the cost and the comfort. The cost has to be minimized and the comfort has to be maximized. So we want to optimize both the objectives, cost and the comfort. And this is basically called the multi-objective optimization. So basically, you know that if in case of multi-objective optimization, there are two objectives and there could be more than two objectives, and starting from two, it could be more than two as well. And we will be getting a set of solutions on the Pareto optimal surface. And it basically produces a set of non-dominated solutions, which is called the Pareto front. And now we can provide the user this Pareto front, and user can basically select a single solution from the Pareto front. So this is the definition of multi-objective optimization, that there are some decision variables and there are some inequality constants and the equality constants, and you have to simultaneously optimize some objective functions. And you know it is not possible to have a global solution, and rather it can produce a set of trade-off solutions, which is called the Pareto optimal set. So you can see there are two objective functions, F1 and F2, and we are maximizing these two objective functions. And as a result, we are getting a set of optimal solutions, a set of Pareto optimal solutions. So if you compare solution 1 and solution 2, solution 1 is better with respect to F2, but solution 2 is better with respect to F1. So solution 1 cannot dominate solution 2. Solution 2 also is not dominating solution 1. So these two solutions are called non-dominated solutions. But if you compare solution 5 and solution 2, for both the objectives, solution 5 is having lower objective functional values compared to solution 2. So basically, you know that solution 2 is better compared to solution 5. So we propose this architecture. So here again, we are in the input side, we are considering the text documents, images, and the videos. And now from the videos, we are again, we are separating the videos into two parts. We are either extracting the key frames, which will form our image set, and there is an audio signal. So the audio signals will be translated, we will be generating the speech transcripts of the audio signals, and the speech transcripts will be added to the text set. So we'll be having the text documents as well as the speech transcripts. So that will be the text set. And then this, the key frames and the images will be added, and we will have the image set. Then by using this algorithm, which is already I should mention to there was a question last time only. So by using this algorithm, we are projecting this text set and the image set into the shared space. Then we will be generating the text vectors and the image vectors. And these are the steps of the multi-objective optimization: population initialization, generating new population using genetic operators. So how the key frames are identified? So key frame identification, there are different algorithms. So what you can do is that, Raji, maybe you can extract all the frames, okay? And now you can basically, for each frame, you can basically, you can find out each frame will be a kind of image. So you can extract the image vector by SNet or VG19, and now you can cluster these image vectors. So then, images will be clustered into different groups. So one group means the sum of images are or the frames are similar. Then from each cluster, you can basically select the cluster center as the key frame. So this is one approach that can be easily done. That all the frames will be clustered in the vector in the image space, and then from each cluster we can select an important frame as the cluster center. The cluster center will be selected as the key frame. Or the other approach could be, that maybe we can at equal intervals we can select some key frame. Like that suppose if your video is of is of 2 minutes, then maybe you can decide after 30 seconds you will be selecting a key frame. So that is another possibility. So we are generating these text vectors and the image vectors, and then this step I have discussed in the last class also. There is a population initialization, which is here. So basically we are doing clustering based. That these image vectors and text vectors are clustered together. Then there are some genetic operators. We are merging P and P dash together. Then we are selecting the best P solution using non-deterministic sorting and the crowding distance. And this is a kind of a loop. So this loop is executed for many generations. Finally, when the maximum number of generations is reached, we obtain the parent-optimal solution set. And then each in the parent-optimal solution set, basically in the final parent-optimal front, there are many solutions. So each solution is a way of basically is a combination of some text sentences and the images. So finally, any of these solutions can be selected as the final summary. This is the proposed model. We propose a novel multi-object optimization-based differential evolution technique to tackle the TIVS task. So this is our the task. So here, as I mentioned, that K-midwife algorithm is applied. On the text side, we are separately applying K-midwife. On the image side, we are separately applied the K-midwife. So we are forming the clusters. In the text side, there is a clustering approach. In the image side, there is another clustering approach. So basically, the solution is having two components: text component as well as the image component. So basically, in the text side, we have the text cluster centers. In the image side, we have the image cluster centers. So basically, we are applying the K-midwife algorithm in the text side as well as the K-midwife algorithm in the image side. So we are applying the crossover operations, and we are generating some new solutions. Solution 1 and solution 2 are basically crossed over, and then we are generating new solutions. Similarly, we are applying polynomial mutation, insertion, and the deletion operation to generate new solutions. And finally, all the initial P solutions. And after crossover and mutation, we are generating new set of P solutions. So these two mod P solutions are merged together, and then 2 into mod P solutions are ranked to generate multiple fronts based on non-dominance in the objective space. And then basically we are applying the non-dominator sorting and the crowding distance on this 2P number of solutions to generate top P number of solutions for the next generation. So this proposed model is executed until maximum number of generations is reached. And after the stopping criteria is met, we proceed with post-processing the parent-optimal solutions. So there are two types of objective functions: summarization based and the clustering based. In the summarization based, you can see that we have the saliency of text by redundancy of text, saliency of image by redundancy of image, and the cross correlation. And the clustering based, we have the text we can calculate the PBM index on the text side, PBM index on the image side, and the cross correlation. So saliency stands for SAL stands for saliency, RED stands for redundancy, and cross correlation stands for cross-modal correspondence. So basically, these are the two possible objective functions. So we have this saliency by redundancy in the image, saliency by redundancy in the text, and the cross correlation. And the clustering based also, we can easily calculate PBM index in the text side, PBM index in the image side, and the cross correlation. So cross correlation stands for the cross-modal correspondence. So these are the, you can see that these are the objective functions. So we are computing the similarity, cosine similarity between the cluster center and all the points which are in a cluster center. So this is the saliency of a particular modality. Redundancy is basically the cosine similarity between two cluster centers. So it is a cosine similarity between two cluster centers that has to be maximized because we want to make the cluster separated. And the cross-modal correspondence is basically this one, that we want to basically maximize the similarity between the image cluster center and the text cluster center. So post-processing, you can see that sentence clusters, the sentence cluster centers are considered to be extracted text summary. For image summary, we select the non-keyframe image centers and append the summary with the images. So basically, we are applying some post-processing, as I mentioned earlier, that some more images are added to the image summary, and one particular video is selected as the video summary. And we compare this with different baselines. And these are our results. So you can see that when we are our multi-object optimization based approach provides the maximum rules values, and also the image precision, image recalls are higher compared to all the other, and video accuracy is also high. So this is your sample summary. You can see that here this is basically the summary, and this is the image summary, this is the video summary. So you can see that we are able to produce the multimodal summary. So just one concept that I would like to mention, that in case of multimodal summary, maybe sometimes the image and the text are maybe somehow complementary to each other, or maybe they could be supplementary to each other. Means the information information present in the text modality is maybe the similar to information present in the image modality. So there is called the supplementary summarization. But if suppose the image modality contains some information which is not present in the text modality, then that is called the complementary information. So based on this complementary supplementary information, we can basically divide the, we can, what we can do, basically we can propose a new task which is called the supplementary complementary multimodal summarization. So here input is the set of documents, set of images, and the set of videos. And we would like to generate a multimodal summary, which is having some text summary, image summary, and the video summary. And basically now this image could be complementary to the text summary, or it could be supplementary to the text summary. There are two types of enhancement. So either when the adjacent modality completes the central modality by contributing alternate but relevant information, that adjacent modality is a complementary visual enhancement. So like as I mentioned, suppose something is present in the text and something is present in the image. So if the image is having, image is having some information which is not present in the text, then that is called the complementary visual enhancement. But if suppose when the adjacent modality reinforces the facts and ideas present in the central modality, so like suppose the maybe the text modality is the central modality, but the information present in the image modality is a supplementary to the text modality, then this is called the supplementary visual enhancement. So there are two helper functions: quality estimation function and the diversity estimation function. So the quality estimation function basically checks the quality of the additional modality with respect to the central modality. So there is a central modality and there is an additional modality. So we are checking the quality of the additional modality with respect to the central modality. So takes as input an entity to be evaluated for enhancement, subject to a central modality based summary. And it basically gives us quality score ranging from 0 to 1 based on relevance to the text summary, 0 being no relevance, 1 being highly relevant. And diversity estimation function, it basically takes as input an entity to be evaluated for enhancement subject from the set DMOD to a central modality based summary and gives a diversity score ranging from 0 to 1 based on information overlap with the text summary, 0 denoting high overlap, 1 denoting no overlap. So we have a formal definition. So basically enhancement candidate means an item in the adjacent modality input. So that satisfies the this quality function. So if suppose the image information is having some quality. So first of all, when can we consider a additional modality? So the modality should have sufficient quality. Then only we can consider the particular modality for generating the summary. So basically an item in the adjacent modality input that satisfies the condition is considered as an enhancement candidate where 5 is the quality screening threshold. And now basically depending on the, if it satisfies the quality, now there are two conditions, diversity. So if the diversity is less than a threshold, then this is a supplementary type. If the diversity is more than a threshold, then it is a complementary type. So basically there are two situations. So one is basically, enhancement, either we can, that we have to consider the basically the quality. If quality is greater than a threshold, now we have to go for the diversity. If the diversity with respect to the central modality is less than some threshold, then this modality will be considered as a supplementary modality. Otherwise, if the diversity is greater than some threshold, then it will be considered as a complementary modality. So you can see this example. Suppose our text summary, central modality is our text summary. And here, this is the summary, the Russian airliner which crashed in the Sinai desert, killing 2 to 4 people, was downed by a bomb. Analysis of the black box recorders indicates the plane had been carrying 217 passengers, including 17 children and 7 crew members. Families of the passengers have gathered at St. Petersburg airport as bodies begin to arrive back in Russia. So here you can see that whatever is written here, that is also visible in these images. So like from these images, you can easily see that it's a plane crash. So basically the whatever is written here, that is basically supplemented by these two images. So this is called the supplementary enhancement. But if you see this summary, like relatives of the victims created the memorial at the St. Petersburg airport, ISIS is claiming responsibility for the crash, with both Russia and Egypt deny it. So this information was not present in the central text summary. So this information is kind of a complementary information. So this is example of a complementary enhancement, where the information present in the images are not present in the text summary. So then it is called a complementary enhancement. But if the information present in the text is also present in the image, then this is an example of the supplementary enhancement. So we also proposed a multi-objective optimization based technique. We basically extended our previous work. So here again, you can see this is an overall flow chart. So we have the videos, we have the images, we have the text. So from the videos, we are now extracting the audio signals and the keyframes. So the keyframes are added with the image set, and the audio signals are translated into speech transcripts, and the speech transcripts are added to the text set. Now we are basically projecting this text set and the image set in the shared space by using the previous approach. So that way we will be generating some text vectors and the image vectors. And then there are two processes. So we are passing through the Gray-Wolf optimizer. Here we have used the Gray-Wolf optimizer as the optimization technique. And we are basically clustering the text vectors and the image vectors together. And this is basically called global coverage text format. So in this clustering process, we are considering both image vectors and the text vectors. And now there is a visual enhancement engine. So here by using this process, we are able to generate text summary. And after this, there is a visual enhancement engine. So this visual enhancement engine will basically select some supplementary images and some complementary images. So with the text summary, it will add some supplementary images and also some complementary images. And we will be also adding some videos with them. So basically this way we are basically generating the summary. So this is our proposed architecture. So you know that for the global coverage text format, it is a clustering based approach. Here Gray-Wolf optimization is basically used for clustering the text vectors and the image vectors together. And it is a multi-object optimization strategy is adopted. Here there are three objectives: saliency, homogeneity, and redundancy. So saliency is nothing but the similarity between the cluster center and all the other vectors which are in a particular cluster. So it is a kind of a compactness. So it is a cosine similarity between the cluster centers and all the points in the cluster. So basically, you know that this is the saliency. Saliency is nothing but the compactness. We have to maximize the saliency because we want to make all the vectors very much similar to the cluster center. And the redundancy is basically, you can see this is the similarity between two cluster centers. So we need to minimize this. So saliency has to be maximized, redundancy has to be minimized. So the heterogeneity is that heterogeneity, we have introduced another objective function. So this heterogeneity basically considers that when you will be generating clusters, there will be some image vectors as well as some text vectors. So it should be heterogeneous cluster. So not only text vectors should be present, but it should also contain some image vectors. So after that, we are also the second stage is basically visual enhancement of text summaries. So by using this process, basically we are basically generating some supplementary images and the complementary images. So using this global coverage text summaries, appropriate tag for supplementary and complementary enhancement is assigned to each image and keyframe. Then one-shot population-based selection technique is adapted to select the appropriate enhancements to obtain a population of the fittest multi-objective enhanced summaries. And then the post-processing steps are applied to visually enhance the multimodal summaries. So you can see that here, you can see that this is the approach. So by using this approach, we are basically determining whether an image is of supplementary nature or complementary nature. So basically, our target is to select select some images which are of complementary nature and some images which are supplementary in nature. And you can see these are the plots of the objective spaces for one generation. So how basically you can red color denotes the rank 0 solutions and blue dots represent the rank 1 solutions. And you can see that gradually there is a convergence. So we are able to produce the better solutions. So we compared this approach also with different approaches. Only like we have also compared with the unimodal approaches. So with only using the text information. So these are the scores. So you can see that our proposed approach basically mostly basically attains the that when we are having these two objective functions, saliency and redundancy, that time only it is giving the best highest root score and root zero score. And saliency, redundancy, heterogeneous, these three objective functions are also giving us the best root scores. So yes, so this is we have also done some human evaluation, because as I mentioned that another objective of multimodal summarization is to enhance the user satisfaction. So like as I mentioned that when we are reporting the summary, if you are only reporting the text summary, maybe user will not be satisfied. So in that place, if we can somehow report the images as well, like nowadays in the newspapers, news reporters are not only writing the description of the event, but also some images are also shown in the newspapers. So basically these images are shown just to improve the user satisfaction. So user satisfaction plays a very important role here. So we have also measured this user satisfaction by using human evaluation, because there is no qualitative measure to measure the human satisfaction. So we have measured the human satisfaction by using basically this human evaluation. So you can see by only seeing the text summary, our scores are human satisfaction is 3.6, 3.66, 3.60. And if you are using the complementary enhancement and the supplementary enhancement, then the scores will become 4.20 and 4.05. So next, I will stop now, but just one point that we have also done multimodal tweet summarization. So in case of multimodal tweet summarization, we have considered the tweets as well as the images which are associated with the tweets. And then we are classifying these tweets into two categories, situational and non-situational. Because as I mentioned that we are not interested in tweets which contain some emotional or sentiment information. We are interested in tweets which contain some, some information related to the rescue operation. So basically, we are classifying the tweets in two categories, situational, non-situational, and then we are summarizing the situational tweets. And those are given to the rescue team, and rescue team can start doing some rescue operations. So here we have used this binary optimization technique, and we have simultaneously optimized multiple objective functions: anti-redundancy, maximum TS-IDS score of the tweet, maximum length of the tweet, then different tweet scoring measures, whether the tweet is important or not. So how many times the tweet is retweeted. So that gives the importance of the tweet. So this retweets code we have considered as a information. Then BM25, this is also this is another way of measuring the quality of the importance of the tweet. So all these objective functions are simultaneously optimized by using the search capability of binary differential evolution. So you can see that this is some examples like multimodal tweets, the corporate donations for Hurricane Maria relief top $24 million. So you can see these are some, these are some multimodal tweets. And what we have done, we have basically generated the captions of these images. And those captions are added to the tweet. And then that way you have basically enhanced the context of the tweet. Because tweets are very short, it is having some character limitations. But if we can generate the captions of the tweets, and if the captions can be added with the captions with the tweet, then that way we can basically enhance the context of the tweet. So then we have developed a multi-objective optimization based technique. So as I mentioned that we are basically generating the dense captions. So dense captions means a paragraph description of the image. Like if this image is given, then the dense captioning will be a white truck on the road, white truck parked on the street, the shirt is red, the graffiti on the side of the truck, a window on the bed, a man wearing a black shirt. So this way we have generated the multiple captions or the dense captioning of the images, and then those dense captions are basically added with the tweet, and that way we have enhanced the tweet context, and then we calculated the different objective functions. So yes, so I think I should stop now. And now, so as I mentioned that in recent years, we are working in the field of multimodal summarization, and you can see our publications which are in top tier venues, like we are regularly publishing in top information retrieval conferences like SIGIR, which is a A-star conference, then ECIR, which is also a category A conference. So yeah, we are basically working in the field of this multimodal summarization. We are now working on some abstractive multimodal summarization systems. So yes, so so basically, Santosh, you are here now.
Yes, ma'am.
Yeah, so if you have any questions, you can ask me. Otherwise, my student will show you the the demo. Okay, so there is a question. So ILP, integer linear programming. So integer linear programming, is this Gurobi optimizer. So you can use an optimizer called the Gurobi optimizer. So this Gurobi optimizer is freely available. So you only have to formulate the integer linear programming framework. So that requires that you have to fix the variables. You have to fix the, you have to basically fix the constants. You have to fix the objective functions. And once these definitions are fixed, you can provide these definitions to the Gurobi optimizer, and then Gurobi optimizer can help you in solving this integer linear programming problem. Okay. So in my slide also, I will be sharing my slides with you. So the link for the Gurobi optimizer is given. So this integer linear programming can be applied for solving any kind of optimization problem. Like here, mostly we have used the multi-objective optimization problems. That's why integer linear programming was not used. But if somehow you can combine all the objectives and you can have a single objective function, then easily integer linear programming can be used to solve that particular problem. So Om Prakash is having, will you please give some details? Okay, this is the, yeah. Madam, do you need to give some basic textual information related to image for summarization image? Not necessary. As I mentioned, no. Either you can process like our approaches. In our approaches, we have not used like initially the methods that we have discussed. In those methods, we have treated images separately. Like we have not extracted the textual description of the images. So image is a separate modality, text is separate modality. So no textual description of image is required. So, our approaches, what I mentioned, which are published in SIGIR, image is basically one modality and text is another modality.
Ma'am, I have a question.
Yeah, please ask.
Ma'am, if I'm creating a corpus for summarization, we will need ground truths, right? So to create this ground truths, what is the minimum number of annotators that should be there sufficient both
So
for
mostly, in
annotations
most
and
of the
evaluation?
papers,
Hmm.
yeah, most of the papers are reporting 3 annotators, because you have to also see the agreement between the annotators, no? So
Yes,
agreement, because it should be odd number, and minimum 3, because 1 you cannot rely, and
Of
2
course.
is difficult, because if there will be a mismatch, then whom to rely on? So that's why 3 is a good number, because 3 in general, for most of the annotation tasks, you can see any NLP papers, they're reporting the 3 annotators. And then the majority of them is basically used as the final summary.
Okay, okay, ma'am. And can those same annotators, can they be used for evaluation also, or will that give a bias to in the human evaluation?
Evaluation means the human evaluation.
Yes,
No,
ma'am.
human evaluation, no, I think they can be easily used, because human evaluation, what we done is basically, human evaluation can be done on the textual summary as well as the multimodal summary. But they
Yes.
can be, they can be used because they have seen the original document. I think they would be the better, they are the best person to evaluate the summary, generated summary also.
Okay, okay. Thank you, ma'am.
Okay, I think Santosh, maybe now you can start. You can share your slides.
Yeah.
You can share screen. So Santosh will now show you a demo, like how we have developed this, multi-object optimization based summarization system. So he will show you the demo.
Okay. So good evening to all of you. I hope the screen is visible. Is it?
Yes,
Can
yes,
somebody confirm?
yes. You are audible also. Yes.
Okay, ma'am. So we have used the multi-objective clustering framework for the one of our work that is on the scientific document summarization, and it is published in Applied Intelligence. So the dataset of the scientific document summarization, it is already released. It is already conducted in the two shared tasks. One is on the SIGI 2019, and another one was conducted in the EMNLP 2020. So this dataset is publicly available. So what we have done, we have applied the multi-objective clustering-based framework for the scientific document summarization. So this dataset you can also utilize for your further work. So it is freely available. So the dataset basically contain the paper from the computational linguistic domain, means ACL paper, and the dataset contains the some ACL paper and all the the citance paper, means the paper which have cited the original paper. That information is also given. Suppose there is a single paper and 20 people have cited the paper, so that information is given. So the when the author cite a particular paper, then he or she writes something about the reference paper, so that the text is also given. That is known as citance. So we have to utilize both the things, the reference paper information and the citation information to summarize the scientific article. So what we have done, like as you can see, these are the test sample. So in the annotation section, they have given the full information, like the text also. How many paper have cited the original article, and the text is also given. So what we have done, we have extracted the the text from the reference paper, and also the citance text also. Citance text means that text which is written by the citing paper. So like as you can see, we have already pre-processed the text file, and we have gathered the citance information. So as you can see, these are the actual the text that we have to cluster. So initially what we have done, firstly we suppose our paper has the 1500 sentences, the reference paper has 1500 sentences, and the 10 paper has cited the original paper, and and they have written the one sentence about a particular paper, so there are 10 sentences. So what we have initially done, we have done the citation contextualization. Means the citation contextualization means what, we are using the citations text to identify the important sentences from the reference paper. So how we have achieved it, accomplished it, we have used the word mover distance. We are picking the one citation sentence from the citing paper, and finding the word mover distance of all, and with respect to all the sentences in the actual reference paper. So using the in this way, we are doing the for the all the citing paper. So in this way, we are sorting all the sentences of the reference paper in terms of the word mover distance, and based on the ranking, we are picking some important sentences from the reference paper. So in this way, suppose we have the 1500 sentences in the reference paper. Now we have reduced our number of sentences up to 200 sentences. Now we have the important 200 sentences. Now we are working on that to summarize summarize the scientific paper. So this we have already gathered. So that suppose so this is the sentence, as you can see here. Let me show you. So these are the sorry, this is the WMD matrix. Okay, so these are the sentences after we have obtained it after the citation contextualization. So in this paper we have chosen the top 58 sentences for the summarization. So now we will deal with these sentences we will form the summary out of these sentences. So now what we are doing, we are using the differential evaluation based clustering technique, multi-objective clustering technique. On the back end, we are using the k-medoid clustering algorithm. So as a distance function, we are not using the Euclidean distance, we are using the word mover distance when applying the k-medoid algorithm. So why we are taking the k-medoid algorithm? The advantage of using the k-medoid algorithm is that when we pick a cluster in the k-medoid algorithm, the cluster center will also be a sentence only, because we have to pick the cluster center out of the document only. So this is the advantage when we are using the k-medoid algorithm. So initially because and we are using the k-medoid algorithm with word mover distance as a similarity measure. So what we have done, we have initially finded out the word mover distance between the all sentence with respect to all other sentences, as you can see here. So let me show you. So this is word mover distance matrix. Let me show you. So suppose there are these are the 58 number of sentences. So we have calculated the word mover distance between all sentences and respect to all other sentences. So the word mover distance between the sentence itself will be 0. So that's why the diagonal is 0, as you can see. So these are the nothing but the word mover distance with of the all the sentences corresponding to remaining sentences. So we are using this information when we will do the k-medoid clustering. So that time we will utilize this information. And apart from that, as you can see, the title of the each paper has the corresponding title also. So that is the, like, as you can see, this is the title of the paper: word reordering and a DP based search in the statistical machine translation. So what we have done, we have also finded out the word mover distance between the all sentences and the title also. So why we are doing this? Because we want to utilize this information also when we will form the summary. So as you can see here, these are the all the sentences, and for all the sentences we have calculated the similarity of the sentences with the title of the paper. So these are the nothing but the word mover distance. Okay, so we will utilize this similarity with the title information later on when we will form the summary. Okay, so now to feed this information, we need to represent all the sentences. So we have utilized the BERT representation to represent all the sentences in a form of vector. So as you can see, we have generated the sentence vector. So these are the vector. So there are the as you can see, there are 58 number of sentences in this particular paper. So we have the 58 number of sentence vector. So you can use any other embedding also. We have used the BERT embedding to represent all these sentences. So apart from that, scientific BERT can also be utilized here, which is trained on the scientific corpus. So and this corpus has a 3 kind of the gold summary, like community summary, human summary, and the abstract of the paper itself. So so these are as you can see, these are the initial task that you have to do, like you can say the pre-processing step that we have done with all the, once we have all these things. So now we will utilize all this information in our approach. So as you can see, we are feeding this detail in our algorithm. So we are initially extracting the data, actual summary, the title vector, WMD matrix, and WMD title. We have already calculated, I have already told, WMD matrix, word mover distance matrix, that we need between the all sentences, the title vector. Similarly to as we have generated the sentence vector, in the same way we have generated a title vector also. So these are the information that we have already feeding to our algorithm. So initially what we are doing, so as you can see, we are using the differential evolution based clustering. So these are our problem definition. So as you can see here, So we have the we are feeding the solution length and the data and the text data and the WMD matrix, and we are using the two different objective function. So as you can see here, there are F1, F2, two objective function. The one is the PBM index and another one is the XB index. So these two objective function is basically used to measure the goodness of the cluster formed, and they basically measure the compactness and the separation. In terms of the compactness and the separation, they measure the cluster quality. So when we during we are using these two objective functions that has to be optimized simultaneously when we will form the cluster. Okay, so as you can see, so this and similarly the problem then we are feeding the problem ZTT is defined here, as you can see here. So we are because we are using the on the backend we are using the because we are using the multi-objective optimization approach. So we have to use the non-dominated sorting also. So here we are define the function of the non-dominated sorting, and then this function has the how to generate the individual. So we are initializing with the evaluation. So here we are using the differential evaluation based approach. We have already defined the fitness count and the what is the will be the population size and everything. So initially we are generating we are initializing our population randomly first, and then after generating once the population, we are using the self-organized map here, as you can see here. So firstly we are generating we have initialized all this detail. So all of you know the NSGA2 algorithm we are using for the optimization purpose. So as you can see here, so initially we are generating our initial population, and using that population we are using the training the self-organized map. So SOM is an unsupervised technique which basically used to map the higher dimensional data into the lower dimensional. So we are using that to map in the lower dimension. Then we are using this information to create the further childrens of the. So we are using the like the other differential evolutionary approach, the like genetic algorithm and PO. So this process, the D is also has the like crossover and mutation operation. So we have we are using the crossover and mutation operation to create the further children. And in this way, we are this is the iterative manner we are forming the next solution. Okay. So and at the same time, when we are forming the solution, we are maximizing those two functions like the PBM index and XB index, and we are forming using the non-dominated sorting also to get the Pareto optimal front. Okay. So as you can see here, so here we are once we are getting we got the suppose we got the Pareto front one. So out of the front one, what we are doing. We are scoring the sentences in a particular front. There will be there will be a solution. So within the solution we have the clusters. So now what we are doing within the clusters, we have the only the text the sentences. So we are scoring the sentences. So how we are scoring the sentences, as you can see. So we are using the different feature to score the sentences within a particular cluster, like the sentence length, as you can see. The sentences which are longer in length, we will that can be important for the summary. Then apart from that, we are the sentence position of we are using the sentence position information also to form the summary. Similarly, as I have already mentioned in the starting, we have already calculated the similarity of a sentence with the title of the paper. So we are utilizing this information to score the sentences. And then anti-redundancy on information is also we are using. This is basically the aim of this function is used when we initially pick a sentence. Then we ensure the next time when we are adding a sentence to the summary, so that the sentence which are already included in the summary, that sentence should be dissimilar. Means the aim of the redundancy function is that all the sentences in the summary should not be related with each other, because the property of a good summary is that it should cover the maximum information, and that can only be possible when all the sentences will be independent to each other, means they should not be similar to each other. So that's why we are using this function anti-redundancy also. So based on these sentence scoring, which as you can see, like the sentence length, sentence position, and then we are doing some apart from that, we are using some weighted combination of these. Like we are calculating the score. Like as you can see, we can use a single feature also to form the summary. Apart from then, we can use the combination of this feature also to score the sentences within cluster. So in this way, we can do the ablation study also, which feature is the important to form the summary in this way. So once we have done all these things, so based on the we get the final score, and based on the score, we are picking the sentences from the summary. So apart from that, we have also ranked the clusters also. So suppose we have the 5 clusters. So from which cluster we should form the summary. So to that to accomplish that, we have done the ranking among the cluster. So we have calculated the first the document center. Document center means suppose we have the 100 sentence. So we are calculating the word mover distance of every sentence with respect to all other sentences and taking the average. So the sentence out of the 100 sentence which has the least average word mover distance, that will be treated as a document center. So now we have the clusters, and because we are using the k-medoid algorithm, so centroid of the cluster will be also a sentence. So we are ranking the clusters in based on the word mover distance between the cluster center and the document center, and we are sorting it. So the cluster which has the which will be the closest to the document center will be assigned higher rank. So we are in the ranking order, we are visiting the cluster and forming the summary. So at the end, we will get the predicted summary, as you can see here. So as you can see, like here we have the predicted summary for this paper, and these are the actual summary. These are the actual summary, and this is the predicted summary of the paper. And to evaluate the goodness of the quality of the cluster, what we are using the Roo1, Roo2, Roo-L score. So as you can see here, these are the score. So this is the Roo1 recall score, precision score, and F1 score. And this is the unigram measure. Roo1 is the unigram match between the reference summary and the generated summary. Roo2 is the bigram match. Roo-L is the longest common subsequence. Based on the longest common subsequence, it is matching the sentences between the generated summary and the ground truth summary. So, and this is the summary length, because there is a constant of the when you are using the scientific document summarization. Yes. Yes.
Sir, please share your link, the notebook link. We are asking, people are asking for that.
Okay. So
Can you see the chat?
Okay. So apart from that, we have also used the Roo3 and SU4 score. So in the most of the scientific document like summarization problem, most in some of the cases, in some of the paper, the people use the Roo3 and the Roo-SU4 also. So this is the trigram match, and SU4 is the skipgram unigram match between the actual summary and the generated summary, and 4 means the up to the length of 4. So in this way, we have generated the summary of the scientific article. So this is purely based on the multi-objective optimization based approach, where we are using the scientific optimizing the 2 objective function, PVM and XB index, and we are using the optimization capacity of the differential evaluation as an underlying optimization strategy. So you can, for more detail, you can go through this paper, and it is now available. So we have, and apart from that, if you want to download the data set, so it is publicly available. So can be, so I have not shared the notebook, but the code is publicly available. So can I share the code over the Google Drive? Will it be good, ma'am? Because
Yes, I think they are asking for the notebook. Hello?
Yes, ma'am. This we can share the code like through the GitHub or the Google G Drive. So a notebook, it is on our currently this code is now on our server, IITP server.
Okay, so then maybe you can keep in your GitHub and then share the GitHub.
Yes, that can be possible, ma'am.
Yeah, and also the dataset link, you please type in
So
the chat
dataset
box.
link is I'm sharing. So dataset is publicly available. Anyone can use this dataset. So any question, please ask. Feel free to ask. I'm sharing this.
Santosh, you have some more time. You have to
Okay. So can we can we discuss?
Maybe you can show the step by step the approach.
Okay.
That Implementation maybe you can show.
Okay, okay, okay. So as you can see here, like initially what we are doing, we are reading all this information. So as I have already said, that so get info function, what is the what we are doing here. So let me show you. So we have already generated the sentence vector, actual summary, title vector, and the word mover distance similarity and similarity with the title. So we are using all this information. So we are reading all this information, and initially we are reading all this information. We will utilize this information for the further in the
How
further.
are you calculating WMD? That please also show.
Okay, okay. So this is the in this way we are using the generating the word mover distance metric, as you can see. So we are using the Google News Vector Corpus, the 300. It is publicly available, so you can use this embedding. So we are using finding the difference, the word mover distance between each line, and we are storing it in a text file. As you can see, the distinct important word mover distance.txt, we are storing it here. So in this way, using this information, we have using this code, we have generated the word mover distance matrix, and this is the word mover distance matrix in the form of txt and in the form of CSV also. So this is the word mover distance matrix. And similarly, we have calculated the word mover distance matrix between the sentences and the title also. So here is the word mover distance between the title and the sentence. In this way, we have calculated. Okay. Now we are done with this. Next step is, now we are simply we are feeding this information, like get info function is reading all this information, data, actual summary, title vector, WMD matrix, WMD title, file path, all these things. So now actually we are starting from here, like the ZT3 definition, the maximum length of the solution, this is already defined. Data is nothing but our sentence vector. Text data is the nothing but about our textual data, and the WMD matrix. So in the ZT3 definition, as you can see here, so let me show you. Okay, so we are forming the problem, like the ZT3 class has the like the two function, the F1 and F2. Function F1 is representing calculating the PBM index, and the function F2 is calculating the Zabin. So these two are the well-known objective function, basically which is used for to calculate the compactness and the separation of the cluster. These two functions are used to evaluate the quality of the cluster. So then we are now here we are using the differential evaluation technique, like the evaluation class, as you can see. So that means we are giving this info, like the problem, number of generation. We have already initially decided number of iteration evolution, and the mating pool size, and the document path. Document path is the only the path where our data is stored. So we are initially creating the initial population. So to create the initial population, so we are using this this code, like the utils. So let me show you. So here the util function is basically on using the NSGA2 algorithm. So this is the function to accomplish the non-dominated sorting here. And here basically to select a function from a particular front, the crowding distance is used. So this is the calculate the crowding distance. And this is the function which is called in the evaluation.py to initialize the population. So once we have the initial population, so using the initial population, initially what we are doing, we are training the SOM. self-organized organized map. So SOM is the basically a unsupervised technique. It maps the higher dimensional data into the lower dimension. Here we have transformed the data into lower dimension, that is L, and now we are using that data to further create the children. So we are creating the children. So using the crossover and the mutation information, we are further creating the next population. So apart from that, we are plotting the PBM and ZIB index here. So these we are also doing the non-dominated sorting here. So as you can see, so domination definition is written here. So these are the definition of a, suppose we what is the meaning of the non-dominated sorting? Suppose I can give you an example. Suppose we have to pick a flight, and there are two aspects, like we have to minimize the time also and cost also. So there are suppose there are two flight like A and B, and A and B are both are equal in terms of the cost, but A is taking less time as compared to B. So A is dominating B. As you can see here, here in our case there are two objective function, and we have the multiple solution like PBM index and XD index. So we have to sort all the solution based on the two objective functions. So we have to accomplish the non-dominated sorting so that we can get the multiple front, and the best front one will be our best front. So in the front one, all the solution will be non-dominating to each other. Okay, so once we get the non-dominant, like as you can see here, for individual in the final population, in the front, on the final front, we have some solution. So out of those solution, what we are doing now, within the solution we have the cluster only. So now out of these cluster, we are now doing the sentence scoring within the cluster, and also the ranking of the cluster. So now, in order to to accomplish the sentence scoring, what we are doing, we are using these information. So now we are using the these as you can see the feature like the sentence length, and sentence length, the sentence position, the sentence which are coming early in the document will be the important. And also we have given some weight, as you can see at the 0.2, 0.3. So we can use the assign some the weighted combination. We can use the weighted combination of this feature also to carry out the lesson study, and the similarity with the title, and then anti-redundancy. So based on these scoring function, we are scoring the sentences within the cluster. So okay, so now we are getting a complete a final score based on these like the length, position, similarity with the title, and anti-redundancy. As you can see here, we are doing the sentence scoring based on these scoring function. We are getting the score, then high score sentences from the ranked one cluster. Also we are following the ranked order when we are picking the sentences. Initially we will go to the rank one cluster, and we'll pick the sentence which are higher in the score based on these four. Only single feature also can be used, or all the combination of the four feature can be used for the scoring. So for each feature we will get a different kind of summary. Okay, so based on these feature, we are forming the summary. Suppose we are using the four different feature, then we will get the four different summary. And if we are getting the combination of these people, then we can get the another summary. So in this way, one can carry out the ablation study also. So in this way, we have formed the summary, and we have stored the summary that is stored here. So this is in this example, I am showing the how it had been utilized applied on the scientific summarization 16 data set. So there are some other data set also available like 17, 18. That we have applied the similar procedure for that. So in the data set, the ground summary, like ground truth summary, is also given, like the community summary. Human summary is the written by human. Community summary are the scientific or the important part of the sentences from the reference paper only, and abstract is the nothing but the abstract of the paper. So these are the three different ground truth summary that is given in this data set. So now we have the predicted summary also. after doing all these things, the applying the clustering operation, calculating the multiple objective function, now we have the good quality cluster also. And now out of the cluster we have ranked perform the ranking of the cluster also. Now we are using the different features also, and based on different feature we are forming the summary. So this is our predicted summary, as you can see. So once we have the predicted summary, so now we have to evaluate the quality of our generated summary. So to evaluate the quality of the generated summary, so code is here, as I can show you, like sorry. So root to function so one can use this is a like root function is a Python library function. Basically root is mainly used in the summarization to evaluate the quality of the summary. So we have used the root1, root2. So we are feeding the actual summary and the predicted summary to calculate the root score. So what it calculate the root1, root2, root3, root su4 and root l. So we are calculating all these three and dumping all these score in a CSV file. So as you can see that I have already stored here, just to show you. So these are the score for there are 10 sample in the SciSum 16 data set, as you can see here, because the data set was also less. That's why to accomplish this task, like the scientific document summarization, we are using the unsupervised technique. If the data set was large, then maybe we can apply the deep learning based technique also. So here we are using the root score, and we are storing the root score like the root1 F recall precision and F, and root2 recall precision and F1 score. Root L is the basic. Root1 is unigram match between the actual summary and the generated summary. Root2 is measuring the bigram match between the actual summary and the generated summary. Root L is the longest common subsequence match between the actual summary and the generated summary. In the same way, the root3 is the our trigram match between the actual summary and the generated summary, and the root su4 is the basically using the two things like the skip gram match and the unigram, and it is up to the length 4 it is considering. So these are the popular evaluation metric which is mainly used in the summarization. So to report the final score, we have taken the average of all these file, and we have reported the final score for this data set, like the scientific summarization 16 data set. So in this way, we have accomplished the task of the summarization of the scientific document summarization. So all these things we have explained in this paper. So because our code has the multiple dependency and code was a bit large, so we have I have not prepared the Jupyter file or this file, but I can make it this code public through the GitHub or Google Drive. I can share it with all of you. So you can, so feel free to ask if you have any question. Ma'am.
Yes. Yeah, WMD, please explain again. There is a question.
Okay.
So we have time up to 8:15. Okay, Santosh, maybe you can elaborate more on how you are getting the embeddings and distances.
So word mover distance. Okay. So let me go to the word mover distance. So word mover distance is a popular evaluation like a technique to find the similarity between the sentences. So apart from the word mover distance, there are some other technique also, like the cosine similarity, Jaccard similarity, textual entanglement can also be utilized. So and PF-IDF similarity can be. So we have used the word mover distance similarity. So word mover distance similarity, suppose there are two sentences, like the Barack Obama is the president of India, and the president of and also president of United States. Barack Obama is the president of United States, and the president of United States is Barack Obama. So word mover distance represent the find the similarity. So the similarity will be, if the similarity is 0, means the both similar the sentences are similar. So why we are using the word mover distance? Because it uses internally it uses the embedding. So that is why we have used word mover distance. So let me see the questions also. So will you please explain the word mover distance once again? Okay, so word mover distance, as I already said, it uses firstly uses the embedding of each word. So for to get the embedding of whole sentence, we can take the average of the whole sentence. So it is internally it is using the equivalent distance only. So you can one can see the actual paper. So it is using the firstly it is generating the embedding of the sentence first by generating the individual embedding of the word, and then it is finding the equivalent distance of between the sentences. So if the distance is 0, the least the WMD distance between the sentence, maximum is the similarity. So that I hope now it will be clear. So this is the property of the word mover distance. So any other question? So if you have the question, so we can discuss. So is the same okay? Yes, sir. In the code.
So you have to show in the code.
Okay. So as you can see here, so Gensim is the model to generate the word to vec embedding here. As you can see, you have to load this embedding. So this is the Google News vector. So it is a around 4 to 5 GB files. You have to download it, and you can use this it will help you to generate the embedding. So as you can see here, we have already have the distinct important sentences.txt that we have got after the citation contextualization. Let me show you. So distinct important sentences.txt. Okay. So these are the sentences. So these sentences we have got after applying the citation contextualization, means when we have already used the citation of the citing information of a reference paper to discard some other sentences. Like as I've already told, suppose if a particular paper has a 10 citation and the paper has the 1,000 number of sentences. So instead of working on the 1,000 number of sentences directly, we are using the citation sentences. Means the author who have cited the particular paper. And when anyone cite a particular paper, she or he will write something about it. So we are using that sentence and then finding the similarity of that sentence between all other sentences. So in this way, we are using the citing sentences, we are picking the important sentences from the reference. So that is known as the distinct important sentences. Now your question is how to generate the WMD matrix. So now we are feeding this file, like the distinct important sentences.txt file. We are feeding to generate the word mover distance matrix. So as you can see, so we are feeding this file part, like this file, and then we are converting into the lower form and like the splitting it, and then the word mover distance model is here calculating the distance. So I have written the name like it is like the sentence Obama and sentence president, and basically these are the two sentences only. In these two loop, the different sentences are coming. So we are generating the word mover distance between each sentence and all other sentences, and now we are storing that value in F5 file, that is a distinct important sentences word mover distance matrix. So as you can see here, so this is the word mover distance matrix. So these are the word mover distance matrix. So this is for your understanding, I have stored the CSV file also, so that it can be easy to it can be easily understood. So this is the word mover distance. In this way, we have calculated the word mover distance between each sentence and all the sentence. The diagonal is 0 because any sentence will be similar to itself. So the 0 is the maximum similarity. So I hope now you have understood the meaning of the word mover distance.
Sir.
Okay.
It is
Thank you.
clear.
So
Yes, but this is available function or one has to write
yes,
it?
yes, it is publicly available. Word mover distance is a publicly available function.
Okay, and one more question I have about embeddings. So there
Yes.
are various embeddings like glow and fast text and other. So there are certain dimension like what to is 160 dimension and other is 300 dimension. So what is the meaning of that dimension? Means actually how you will explain in English like text, that is this is should be called as dimension.
Yes, yes, yes. So, what in order to word move or distance line, we are using the Gensim package. So then, when you use the Gensim package, so there is a constant that you have to use the word to back only. But if you want to use some other embedding, like if you want to use the BERT or anything else, you can also use that also. You use the other embedding also in order to calculate the word move or distance. That is not the issue. We have used in our case we have used the word to back to utilize this package. So other embedding can also be utilized in the same way. So it is a generic in nature.
So one more thing I want, there other embeddings are available, and one will be it will be clear to one that is which is best after testing. But my question is, there is a dimension mentioned in word to wake 160, somewhere it is 160 and somewhere
What
300.
will be the dimension of 300 dimension? 1
Yeah,
cross
300.
300.
300. So what is the meaning of the dimension? Means what that 300 mention means. Suppose it is 1 to
Actually,
200, then what it is?
actually, the embedding dimension, it is not any hard definition of the dimension. One can explain like the bird, the dimension will be 726. So when we represent a particular word in the the embedding space, so suppose we have let's suppose we have a word dog. So there will be different attribute of a
Excuse
word.
me.
So you can say the dimension of a word, dimension of a particular embedding is like an attribute. Suppose 300 attribute we are recording for a particular word. Like suppose there is a word dog, and we are taking a word apple. So attribute of the dog is a animal. It is an animal. It has the 4 leg. So these are the different attributes. So we don't know the which, because these are the released by the embedding or released by the different embedding are released by like the Google and Facebook. So we can get to know the what is the all the 300 dimension is representative. But definitely these are the attribute only. But what are the 300 attribute?
That I wanted to know.
That
If
is
we can
not.
see dimension, that is at what
Yes,
position it is occurring, whether it is a first word or it is a
yes, yes,
second
yes.
word,
These are
and
the
that
basically
kind
these
of.
are yes, yes, ma'am. These are attribute
Okay,
only.
okay.
Hmm.
Okay, thank you, sir.
Hmm. Okay, ma'am. So I think because I have already discussed everything, so if there will be question, it will be good for me, and so we will discuss. I can discuss with you everything. So if you have any doubt in a particular step, it will be good for me also because I have completed, I think, little bit early.
Yeah, in many of the work which is on summarization, it is seen
Yes,
that
ma'am.
unigram and bigram, this feature, positional features, those make much sense. And embeddings also we make sense to such problems. So
Yes,
my
ma'am.
question is, suppose I want to create embedding from scratch, so how it can be done for a particular feature space?
Yes, ma'am. If you want to create your own embedding, ma'am, then the only thing you have to decide your attributes first, and based on that attribute, suppose that is if that attribute is available, then you can you can use the one hot encoding also, and you can also give the numbers or one hot
Excuse
encoding.
me. Am I audible?
Yes,
Santosh?
Yes,
yes,
sir.
yes. Hmm.
Yes. Actually, embedding to what the question was, no? Ki how to create your own embedding. Uh, in Keras, if you go, there is an embedding layer itself. So after input, once we give, as Santosh was telling, we can give one hot encoding as input, and then there is an embedding layer. And with that embedding layer, so that embedding layer, initially random weights will be given since it's a neural network only. So initial random weights will be given, and if you go give your input and output as the same, so it will train that and it will basically tune those weights, and those weights are your embedded vector.
Okay.
Am I clear?
Yes, yes.
And that's
Okay.
where your question, whether it's 100, 200, 300. So what he suggested, like these are the attributes, no doubt. But these attributes are not known to us. So what features really to extract from those words? So in which, say, unknown dimension it is falling. So those are the different dimensions. So if you want to make that, I want only 100 features or 100 sort of dimensions my word should be represented, then you can go for 100. There is a say 50 also, 100, 200, 300. So like globe, etc. They are available in different formats, starting from
Yes.
20 to 300. But you can always go beyond that also, and but lesser than 25 will be actually too less. So that's how really we create. So creating your own embedding, you can always do.
Okay. Thank you. Got it.
In Keras, there is an embedding layer, so you can just explore that.
Yeah.
I think in some of our earlier demo sessions, because I was not available whole day, that might have been touched on also.
Yes. Means it was shown in many demonstrations. Doc2Vec was also shown. Keras was also shown. But
No, not
my
Keras,
doubt was
that embedding. So how to read from, how to use Globe embedding or FastText embedding,
no.
and then how
Actually,
to create
only
our own
Doc2Vec
embedding.
was there. Glow was not shown.
Globe was shown. Okay,
Not
okay.
shown.
So
Actually, I
not
have
shown. So tomorrow I have
attended all
another
the.
session on
I have
say
attended all the
sentiment
sessions,
classification.
and I
So as
what
I told that, I'm not
yeah.
sure, very sure. So
Yeah.
tomorrow I have another session on say this sentiment classification. So I will try to cover that exactly how to create our own embedding and then do that, and how to take say globe and then do that.
Yes. Thank you.
Okay, that's not a very difficult task.
Okay, so I have actually run the code. It will take at least a few minutes to complete it at least. So because it takes a little bit more time, so that's why I have recorded everything so that it will be easier for me to show at least the stored result. So I have already run the code. So because it depend on the size of the data set, it will take at least 1 hour or 2 hours to complete the whole process. So. So any other question on the whatever I have explained, anything else? If you have doubt, please feel free to ask.
There is no further question, so we can thank Santosh.
Thank you so much,
For
sir.
his excellent work and nice presentation.
Thank you so much, sir. Thank you.
So Dr. Sriparna is also here. So,
Yes.
so thank you, Dr. Sriparna and his team, in fact, for this nice work and so a nice presentation. So, sir, please share the link of the paper once
Yes,
you
sir.
will have
Sir, I am
access. So,
sharing. I am
if you
sharing
can
it.
share the link in the chat box.
So Santosh, you upload the code in the GitHub and then you share the GitHub link with me, huh?
Yes, ma'am. Yes, ma'am. So code is still it will take some time. Actually, ma'am, I wanted to show the live running and the generation of the everything like solution, but it will take few minutes time to complete everything on a single sample also. Should I wait, ma'am, or should I stop sharing the screen?
If you have recorded results, you can just show the
Yes,
recorded
sir. I have
results.
already discussed the recorded result. That's why.
Okay, then we can stop here.
Okay, sir.
Already you have already given them the GitHub link, so if
Yes,
they
sir.
are interested, they can download and go through that code and execute with their own data set or with the data set which is referred there.
Yes, sir. Yes, sir. Okay, sir.
So we can stop here. We can end the session
Thank you.
here. So thank you,
Thank you, sir.
and thank you to all the participants who are still there. So it's good night and see you tomorrow again. Thank you.